Hi everyone, I'm really sorry not being Steven, but I'm trying my best. Welcome all of you here. I'm really proud of our IYPT family that basically everyone has arrived, and even though the parties last night were hopefully pretty strong, you made it. And that's also a very impressive performance, or I'm overtired, sorry. One or two kind of important things. Please do not eat in the room. You are allowed to drink water, but we try to keep clean the room. And you have seen these small plastic flags. Please leave them under your seats, because for the closing ceremony, for the medal ceremony, you have to sit on the right places where you are now. Otherwise, it's gonna be a chaos. And we would like to ask you to help us. And we are here in the Bosch. And I would like to ask the representative of Bosch today to welcome you. I would like to invite Mr. Mátyás Pocsra to the stage.
Good morning. Okay, you can hear me. Great. Dear President Plesch, dear President Ömösei, dear jury members, dear teachers and students. On behalf of Bosch Group in Hungary, I warmly welcome everyone to the finals of the International Young Physicist Tournament event series at our Bosch Budapest Innovation Campus. In this vast 90,000 square meter building, thousands of professionals, programmers, electrical engineers, mechanical engineers, and physicists work daily on mobility technologies that will define our future. These are the advanced technologies that will later become part of the global automotive industry and will shape our daily lives, how we live, work, and move. Here, around this campus, everything is about innovation. Research and test laboratories, vehicle verification area, and state-of-the-art test halls all support development. Our Bosch Budapest Innovation Campus not only hosts technical development, but also 3,600 of our engineers embodying the workplace of the future, an environment that fosters collaborative thinking, inspiration, and creativity for our colleagues. Whether it's solving the variety of exciting research activities or creating the technologies of the future and new innovations, we can all agree that teamwork, collaboration, and creativity are essential for success. That is why we at Bosch proudly support the International Young Physicist Tournament. The competition aims to help practice and master teamwork, responsibility towards one another, creative thinking, and multifaceted approach to high-level problem solving. All of this is essential for the students' future professional development, whether they shape the future as researchers, development scientists, or development engineers and IT specialists. With this mindset, we at Bosch have been supporting future generations for years through our diverse initiatives, including scholarships, internship programs, and sponsorships. I trust that the atmosphere and spirit of one of the most significant European development centers of the Bosch Group and the closeness to innovation will also inspire you today. Congratulations to all of you for the success you attained so far. I also extend my grateful congratulations to your teachers who prepared the teams, whose knowledge, readiness, and experience have helped every student throughout the competition. Let me quote one of our founder, Robert Bosch's thoughts. None of us should ever be satisfied with what has been achieved, but should always endeavor to do better. And with that, I wish you all the best of luck in the final, decisive phase of this competition. Thank you very much for your attention.
Thank you very much, Mátyás, and thank you very much for the Bosch company for letting us having the final in this wonderful hall, which is just perfectly suited for the number of participants being here. I see that some of you are standing on the back, but maybe you can still find scattered places here in the front. So don't be shy and come and see us from more closer. I don't want to speak almost nothing because we have a more and more usual situation of having 4 teams in the final, which makes it a very long final. So I would just like to switch to the normal procedure of starting the very last physics fight of this Young Physicists Tournament. And first of all, I would like to invite the teams to introduce themselves in the order of appearance in the 3rd stage. So please, Team Poland.
Ladies and gentlemen, can everyone hear me loud and clear? Fantastic. We represent Team Poland. Our team is the following. This is Antoni Kujawski, Zofia Lamenska, this is Maksymilian Ogiela. My name is Paweł Ptaszek, and I'm the captain of the team. And we wish you a wonderful physics fight. Thank you.
Thank you very much. As you see, the team of Poland managed to reach the finals with just 4 team members. The opposing team, we have the team from Ukraine, please.
Hi everyone, my name is Anna Bilaeva and I'm the captain of Team Ukraine. Today with me plays Anton Matiasz, Sofia Fiodoskina and also Kyrylo Vladyko, and I wish everyone a great fight. Thank you so much.
Thank you very much. Again, a team with just 4 team members, so it seems to be a winning strategy, just that you know for the future. No, but like they had a different reason. And the reviewing team, the team from Taiwan or Chinese Taipei, please.
Good morning, everyone. We're Team Taiwan. I'm the captain, Lin Junyi. He is Bai Jingren. He is Ye Xuanyou. She is Huang Youjie. He is Luo Dazhao. I wish everyone have a great physics fight. Thank you.
Thank you very much. And last but not least, the observing team from Singapore.
Yes. Good morning, everyone. We are Team Singapore. This is Junxiang, Kang You, Yunze, Christopher, and myself, Hillary. Here's our mascot, Mark, and we look forward to a good physics fight with everyone. Thank you.
Thank you very much. And now we come to the distinguished jury. So those people who will be judging the teams about their performance. We did our best to select the most experienced jurors with the best feedback from students, so that like everyone is as pleased as possible. So can we start with Eric with your introduction?
Test. Good morning, my name is Eric Schattenleib. I'm a former participant and I have been involved in the Swiss organization for about 10 years, and I wish all the teams the best of luck.
Hi, my name is Ann-Kathrin Raab. I'm currently a PhD student at Lund University in Sweden and also former IYPT participant, and I wish you all a great fight.
Hi everyone, I'm Patrick Pence. I am from Hungary. I'm a former IYPT participant in 2018 and 2019, and since then I'm a team leader for Team Hungary. And I have just finished my master's at the BME University where the opening ceremony was held. And I wish everyone a great fight.
Good morning, everyone. My name's Kerry Parker. I teach at high school in New Plymouth in New Zealand, and I've been involved with the tournament at the national level since about 2006. And it's a real honor to be here, and we'll do our best to have great fights.
Hello everyone, I'm Georgi Khomeriki from Georgia. I've been involved with IYPT since 2015. I'm a PhD student in Kansas State University, and I work in cosmology, in higher order statistics, and also in general relativity. Thank you.
Good morning everyone, my name is Vichaya. I'm a physics lecturer at a university in Thailand. I've been involved in IYPT since 2016, I believe, for the first time. Nice to meet you, everyone.
Hello, I'm Sergej Faletic from Slovenia. I teach at the university, future physics teachers, and I've been involved in Slovenian YPT since 2015.
Hi everyone, my name is Xiaoyang Chen. I'm from Canada, so I'm currently a condensed matter physics PhD student at the University of Toronto. I've also been a past participant from 2016. I wish all 4 teams the best of luck today. Thank you.
Hello everyone, I'm Clear Beyond from the Korea, and I'm a professor in engineering department at the National University. So that's another career path that you can go for after you get physics degrees. And I wish all the best for all the teams, and also the teams not on the finals but here. You are already champions just by being there. So be proud of it and have fun. Most important thing. Okay, thank you.
Okay, thank you very much, Claire. Thank you very much for everyone. Yeah, my name is Martin Plesch. I currently work as a researcher in the field of quantum communication and quantum computers in the Slovak Academy of Sciences. And I am also a professor for future teachers. And yeah, I'm also a former participant. And the first time I participated was 1994. So 30 years ago, a long time. Okay, so just before we start to technical remarks, can I kindly ask you all the teams to switch off or put your mobile phones into the flight mode and switch off your connection on the computers. So really put your computers and mobile phones into a stage where no internet connection is possible. And the second thing, we will be strict with time because it's fair and because will be running short on time. So once your preparation stage is finished, then the flight assistants or I will announce it, and your time for whatever speech it is will start running. If you need more time for preparation, you will have less time for presentation itself. And for when you are presenting, when you are speaking, please, once the time is up, finish a reasonably long sentence. That would be great if I don't have to interrupt you and you just finish and we can go further. For the jurors, we have a big jury, but still the mere 5 minutes for question and answers. So please limit your questions on a very short clarification questions, mostly aimed on what was presented in the presentation rather than asking for further explanations. And please avoid questions going like to all 3, reporter, opponent, reviewer, etc. Okay, that's all from my side. So I would like to pass the time to timekeepers and word to the reporter. You have 5 minutes for preparation. Whenever you are ready earlier, we are more than happy to start.
Hello, can you hear me? Czekaj. I think you can start. Ladies and gentlemen, my name is Maksimian Ogiera, I represent Team Poland, and I'm happy to present to you our solution to problem number 6, non-contact resistance. The problem content states: the responsive of an LRC circuit driven by an AC source can be changed by inserting either a non-magnetic metal rod or a ferromagnetic rod into the inductor coil. How can we obtain the electric and magnetic properties of the inserted rod from the circuit's responses? On this video, we can see the view of screen from the oscilloscope, which shows the voltage on our coil. We can see that during inserting the aluminum rod into our coil, the responsive of our circuit changes. Now we are inserting stainless steel rod, and the last one will be the copper rod. Now let's move on to our LRC circuit. So we will have a series connection of the resistor, capacitor, and an inductor. And by knowing the formulas for the voltage drop across all of these elements and governing equations, first Kirchhoff's law, which will state in our case that the current flowing through each of the elements of our circuit is the same, and the second Kirchhoff's law that will state that the total voltage applied to our circuit is equal to the total voltage drops across all of the elements of our circuit. Using these equations, you obtain the damped-driven harmonic oscillator equation, which solution looks like this. However, we can see that the part coming from the general solution is only relevant for small periods of time. And we will, in our case, we will only investigate the steady-state region. Now, when we know the exact formula for the voltage drop across our coil, we can derive the equation for derive the formula for the resonance curve of the amplitude ratio of the voltage drop across our coil compared to the voltage applied to our circuit. We can also obtain the formula for the phase shift of the voltage on our coil compared to the voltage applied to our circuit. And here we can see the theoretical plot of the resonance curves for different values of resistors used in our circuit. Now our measurements for coil in air. So first we did a resonance curve for the amplitude ratio of the voltage across the resistor compared to the voltage from the generator. And by fitting our function, we were able to obtain the values of the inductance and the resistance of our inductor, inducting coil that we used, which will be then needed for further calculations. Now we can compare the results for the coil with ferrite core, and we can clearly see the differences between them. So let's think what happens there. So when the current is flowing through our coil, it generates the magnetic field inside it. And when the core is inserted into our coil, it gets magnetized. We can derive the formula for the coil inductance with a core inside it. And there are three main magnetic properties. One is paramagnetic, which have the relative magnetic permeability slightly higher than 1. Second one, the example is aluminum. Second one are diamagnetic materials. The relative magnetic permeability is slightly lower than 1. The example is copper. And the last one are ferromagnetic materials, for which the relative magnetic permeability is significantly higher than 1. And the example is ferrite. And from this, we have a conclusion that only ferromagnetic materials interact with magnetic field significantly. Now, when we substitute our formula for the inductance of the coil with core, we can obtain the value. We can see that our function fits really well the measurements, and we can obtain the value of the relative magnetic permeability of our ferrite core. We can see that it is in a reasonable range, as we could see before. Now we can compare the results for the coil with copper rod inside, and we can clearly see the differences. Even if we take into consideration the fact that its relative magnetic permeability slightly changes, we still see that our function don't fit the measurements. So let's think what happens there. So when the changing current is flowing through our coil, it generates the changing in time magnetic field inside our coil, which, as we all know, induces the electric field, and due to the Ohm's law, in our rod there will be induced density currents. And as we know from the Lenz's law, these currents will induce magnetic field in such a way that it will counter-react with the changing of the magnetic flux through our coil. And from this we have a conclusion that eddy currents are induced in conducting rods. So, in order to take them into consideration, we will investigate Maxwell's equations in three main regions in our setup. One is rod, second one is inside our coil, and the last one is outside. And by using boundary conditions for the rod and inside border and the inside and outside border,
we assume that there is no charge accumulated at the surface of the rod and no charge accumulated at the surface of our coil. We also assume that there are no surface currents at the surface of our rod because we have density currents, and if we look at very small piece at the surface, there is no current. And we also take into consideration the fact that surface current on the surface of our coil is due to the fact that the current is flowing through the coils of our coil. And from these equations and boundary conditions, we can obtain the analytical formulas for the magnetic field distribution in different regions in our setup. So here is an example of the plot for the values close to the ones in the measurements. We can see that for the really low frequencies, the magnetic field is the magnetic field inside our coil is constant in all of the regions. However, if we increase those frequencies, we can see that the distribution of the magnetic field inside our coil, inside our rod, drastically changes, and it drastically changes with the frequency. Now we can see our boundary conditions on this graph, and now we can compare the results for different frequencies in our circuit. We can see the distribution of the magnetic field, and you can see that with the increasing frequency, the more of the magnetic field is accumulated at the surface of our rods. It is really, it works exactly the same as the skin effect, which is caused by the eddy currents induced in our setup. The eddy currents are also dependent on the frequency, and their significance increases with the frequency in our circuit. And that's why, effectively, the magnetic field is mostly accumulated at the surface of the rods. Now we can calculate the voltage drop across our coil, but integrating over the over the curvature of our coil, the electric field. And we can see that this formula looks exactly the same as the regular formula for the voltage drop across the coil, with the change that our inductance of the coil itself is multiplied by some function dependent on frequency, which will also cause our inductance to become a complex number. And here we can see a theoretical plot for the real and imaginary part of our coil due to the frequency. Now, when we substitute this real and imaginary part to our equations, we can see that the imaginary part of the inductance of our coil behaves exactly the same as the resistance of our coil. And it is the non-contact resistance about which is the problem compensated. Now, when we plot the theoretical resonance curve for different values of conductivities, we can clearly see that the resonance frequencies increases with the rod's conductivities. Now, our experimental setup. It consists of the computer, connected to the oscilloscope and function generator, which were then connected to our LSC circuit. Now our measurement procedure. So by using the code in Python, we were able to control at the same time both the oscilloscope and the function generator. And that's what, and because of that, during the measurements, we didn't have to do anything. Now, in our setup, of course, we used a capacitor and the resistor for the LRC circuit. We used different driving frequencies and amplitudes using our function generator. And we used rods made out of different materials: copper, aluminum, stainless steel, steel, and ferrite. Here are the values of the parameters changed in our setup. We changed the radius of the rods, materials of the rods, and the driving frequencies. Now the results for the copper rods. We did the measurements for different radius of the copper rods inserted into our coil. We can see that for all of them, our theoretical function fits really well the measurements, and from these measurements, we're able to obtain the value of conductivity of the copper that we used. Now we can compare the results for the stainless steel. From these measurements, we were able to obtain both the relative magnetic permeability and the conductivity of the stainless steel that we used in our experiments. And the last one are the results for the different radius of the aluminum rods. We can again see that our fitted functions fit really well the measurements, and from these measurements, we were able to obtain the values of conductivities of the aluminum rods that we used. Now we can compare the results for different materials and the same radii of the rods. So we can see that for this, and here on this graph, we can see that for the strong ferromagnetic materials, such as steel and ferrite in our case, the resonance frequency decreases. However, for the stainless steel, which is a poor ferromagnetic material and it has conductivity, the conductivity has more significant effect. And that's why the resonance frequency for the coil with stainless steel rod decreases the same as for the copper and aluminum, which will only affect due to their measurements due to their conductivity. Now we can compare the results for the different radii of the rods and the values that we obtained of the conductivities. We wanted to check whether the values are correct, and for this we did an independent measurement using high current generator, and by applying current to our circuit with the rod and measuring the voltage drop across our rod, we were able to obtain the value of conductivity. And here we can see the comparison of the theoretical of our results from the independent measurements and the results from our LRC circuit. We can clearly see that they match pretty well the independent measurements. Here is also the relative accuracy of our measurements, and we can see that for the highest radius of the rods, we have and for the smallest radius of the rods, we have significant deviations. The smallest radius of the rods might affect our circuit that because of the small surface, it affects really low the responses of our circuit, and that's why it's hard to measure them accurately. And for the really high radius of the rods, our approximation of the solenoid that we use in our theoretical model might not work the best. To conclude, resistivity, magnetic permeability, and ferromagnetic properties of metals have big impact on LRC circuit response. Due to the fact that metal rods are conducting, the eddy currents are induced in them, and we can see the skin effect inside our rods. We also, for ferromagnetic materials, the resonance frequency of the circuit decreased due to their high magnetic permeability. And by fitting the resonance curve to the measurements, we obtained these visible values of conductivity and magnetic permeability of the rods that we used. Thank you.
So thank you very much for your report. So my first question is, were you optimizing this device? Yes or no?
Yes.
And what parameters were you varying?
We were checking this theoretically.
Okay, thank you so much. My next question is, what frequencies have you used?
What frequencies? We can see on the slide 30 around. So we used from the 100 hertz to up to 200 kilohertz.
Okay, thank you so much. And is your theory using the small amplitudes approximation?
The small amplitude approximation?
Yes.
I
yes
mean,
no?
it's
okay,
partially less, but we'll discuss it later.
Thank you so much. My next question is actually, were you using only series connection, no parallel?
We are using only series connection because we are able to measure the voltage drop across the resistor more accurately than the current flowing through.
Okay, and you were not checking the parallel connection at all?
No, we have the better measurements for the voltage.
Thank you so much. My next question is actually, can you measure the initial magnetization of the rod if it was initially magnetized?
Using our circuit, we checked before the measurements whether our rods were magnetized, and they weren't.
They were not. And if they were, it still is a property of it. You can measure it or you can't.
Using our setup, it will be only shifted by the constant. So I don't see the point.
Yes or no?
We don't see the difference then.
Okay, thank you so much. My next question is actually, have you investigated hysteresis of this problem?
We didn't investigate. For the range of the measurements that we used, the hysteresis is negligible.
Okay, thank you so much. And my next question, can you please open slide 30?
30.
So can you please tell more about the errors for the aluminum and the stainless steel?
The errors are from the fitting functions, fitting values.
And why is it so big for stainless steel?
It's on the logarithmical scale, so it looks like this.
Oh, okay. Okay, thank you so much. That's all from me. Thank you.
Okay, please, the teams have very hard time to prepare themselves for the next stage, and it would be very good if you really calm down till we have finished this round. because they just have seconds and counting seconds on preparing the slides and everything. Thank you very much.
Or something like that.
The time's up.
Yeah, like probably.
Yeah.
It was working before, so.
So you checked before and it was working?
Yes, it was working before, so yep. Something has happened, like it was working. Yeah. Okay, so I actually can start.
Okay, let's start.
So, hi everyone, my name is Anna Bilaeva, and today I'm opposing task number 6, non-contact resistance from Team Ukraine. And according to the task, the responses of LRC circuit driven by an AC source can be changed by inserting either a non-magnetic metal rod or a ferromagnetic rod into the inductor coil. We have to investigate how can we obtain the magnetic and electric properties of the insert rod from the circuit's responses. So let's start with the analysis of the report that was actually visible by us. So let's start with the analysis of the qualitative explanation that was presented. So at first, the phenomenon was actually demonstrated. We indeed were able to see that the responses were changing while we were inserting the rod and when there was no rod actually in it. And also the circuit, which was used by the reporter, was presented. We have actually some doubts about the fact that only the series connection for the circuit was presented, and I would like to discuss why it actually is more efficient than the parallel one. And after that, the qualitative explanation of this effect was actually presented. So it was explained with the usage of the eddy currents, which we fully agree with and consider to be really good. However, one of the weaknesses of this part actually was the fact that no hysteresis was discussed, and unfortunately, in general, it wasn't mentioned in all presentation. So let's move on to the analysis of the theoretical investigation of this part. So at first, we were able to see the analysis of the case when there is no coil, and there is no rod. So we were able to see the fitting of the values for the inductors, and after that, we were able to see the investigation of the distribution of the magnetic field in the core. It was obtained. We think this is a very good advantage of this report, and as far as it allowed the reporter to discuss the skin effect, which actually plays a pretty significant role in this part, and I think that it's a great advantage that it was mentioned here. After that, we were able to see the discussion of the skin effect that I have already mentioned before, and finally the voltage drop of the coil with rod was found. So because of that, the reporter was able to obtain the conductivity and permeability of the system. So I must mention that in general, this theoretical investigation is pretty good. However, there are some weaknesses. So my first question is actually about some losses that are caused by the system. So for example, with the parasitical capacity and other parts. We'll discuss it later during the discussion. Also, we have some doubts about the usage of the small amplitude approximation, since, for example, in the experimental verification of the reporter, we were able to see the case of high frequencies. So, for example, 200 kilohertz, which was mentioned before in the clarifying questions, which actually is pretty a lot. And that means that for this case, these losses and the general non-linearity of this effect may be very important and may cause some deviations, which were not unfortunately discussed. And unfortunately, we were not also able to see the limitations of this theory and also discussion of the optimization, which was done by the reporter. However, it was not presented. And I must mention that in general, the optimization of this problem is very important, and it is stated in the task statement. So now let's move on to the investigation of the experimental part of this problem. So we're able to see the experimental setup. I must mention that it is a very interesting methodics with the usage of the codes in Python. I guess that is an advantage also of this report, allow this experiment to be easier for the reporter to obtain. After that, we were able to see the roles that were used by the reporter, so the different roles, for example, with the different materials, with different sizes and everything else. I guess it's also a great advantage of the report. And after that, we were able to see the experimental investigation of the conductivity and permeability, and finally the results that were measured, the comparison with the independently measured results, which of course is one of the main advantages of this report, since we were able to see how accurate their experimental and theoretical investigation was. However, again, I must mention that I lacked the optimization, also the discussion of the errors, which we all have done during the clarifying questions, and the overall expression of this report is actually the following. You can see that we think that it was pretty good at all these parts, so the qualitative part, the theoretical part, and for the experimental part. So thank you. I invite the reporter to the discussion. So we will start with the optimization. You were mentioning that you are doing it. So can you please explain us?
Okay, so as a part of our optimization, we also use different radius of the rods, for which we discussed why there is a low accuracy for the lower radius of the rods that we use, and why there is also no accuracy of the higher radius of the rods that we use. And we also compare them to our theoretical model assumptions made for the solenoid.
So actually, what is the optimal then radius of the rods and optimal other
so
parameters?
The optimal radius of the rods are the ones, next slide, sorry, 34. So the actual optimal radius of the rods we can see here, which gave us the best relative accuracy. So they are so the rod inside our coil fulfills our coil for the half of the surface.
Okay. And what
so
about the frequency, for example?
About the frequency?
Yes, the optimal frequency for measurements.
The optimal frequency for measurements. So we for all of the measurements, we used the same range of frequencies as we could see
so you were not investigating the optimal one for which the results were.
I mean, we did a resonance curve for different frequencies, and by fitting the values of the conductivity and resistivity, we obtained these values.
Yes, but you were not investigating the accuracy for each of this case, yep?
Yeah, however, I think that for the setup that we use, we also checked how the accuracy of our measurements depends on the slide number 41. We also checked how the different capacitors would affect our setup.
Oh, that's great. That's great.
And we did this theoretically. So by simulating simulating our measurements 100,000 times, because we know the uncertainties of every single measurement of the parameter in our setup. So we used a normal distribution in order to shift all of our points for the value from the normal distribution in the range of the uncertainties of our measurements. And from repeating these measurements 1,000 times, we were able to compare 1,000 different values of the conductivities and conductivities of the rods that we used.
Okay.
And here we can see a standard deviation. The value of the capacitor that we used was around this range. So we can see that the standard deviation from this is for the smaller capacitance is really low. This point. It's 4 to the power of 4 times 10 to the power of -7. And from this we were able to see that for the lower capacitance, the frequency, the standard deviation slightly decreases. However, the resonance frequency of our circuit would significantly increase. And for the measurements that we had, with the higher resonance frequencies, so we will investigate higher frequencies, also the accuracy of our measurements of the voltage using the oscilloscope would decrease. And that's why we decided to use these capacitors in our setup.
Yeah, thank you. That was very important. And what about the number of turns in the coil?
Of the coils,
yes.
It's around 150.
You were not varying it.
No, we will use one coil for our measurements.
And qualitatively, how will it change the result?
How will it change the results? So if we make an example of the more solenoidal coil, so if we use longer coil, it might increase the accuracy for the higher radius of the rods. However, we can still see that the measurements that we did, and for these results, it works really well for the medium radius of the rods.
Okay, thank you so much. So I want to sum up it. Well, I actually, it is very interesting that you were investigating the optimal capacity and the radius of the rods. However, I still think that it is important to investigate such parameters as the frequency and also the number of turns in the coil, since it's also the optimization part. So let's move on to the next part. What about the limitation and the boundaries in general of your theoretical approach?
Okay. So we used Maxwell's equations, as we could see on the slide. So which accounts for the electrodynamics in our system. And these equations, as we know, we use the linear Maxwell's equations, linear parts, and by checking our results also from the independent measurements, we are able to say that this linear Maxwell's equations work pretty well in our setup. So that's why we also did this independent measurements to check the values of conductivities.
Okay, so you saying that there is no limitation of your theory, so it's applicable.
So I mean there is a limitation, and I explained this using the high disaccuracy for the high radius of the rods, because we use a solenoid approximations, and also our coils have a certain thickness, which we also have to include, and we took the distance of from the center of the coil to the arithmetical to the mean range of radius of the rod of the coil.
Okay, yeah, thank you so much. I actually think that I will agree with the reporter, and also must mention that there are some cases for which the nonlinearity in general plays a huge role, and this also may be the reason for the limitations of in our system.
So for what values of the? So do you think that? How do we take into consideration these nonlinear effects, and how can we obtain the analytical solution for this?
Yes, that's actually the reason why I'm asking that. Like the in general calculation and taking into account the nonlinearity of the system is very hard task, and therefore we have to simply limit our theory, and that's why I'm asking that. So let's move on to the next question. Actually, have you like you were talking on the skin effect? So were you taking any other losses into account? So
the skin effect is from we also obtained the skin effect using our theoretical analysis, and it's the main effect that is caused by the conductivity of our rods.
Yes,
so I think we can agree here.
Yes, so okay, so you think that this is the main loss, and you were only taking it into account, and anything else was not.
I mean, we take all the losses that are also used in the Maxwell's equation. Yes, so it's the main one. Yes, it's the main one, loss due to the conductivity.
Okay, well, thank you so much. I probably will agree with you. So let's move on to the next question. So can you please talk more on the parameters of the AC source? So like, were you varying it? Were you investigating it? What about the parallel connection? Why weren't you trying it even?
Okay, so we use the series connection because for the parallel connection, then we would have to measure the current flowing through each of the branch. And we didn't have the setup for the measuring really accurate recurrent, as we can measure the voltage using our oscilloscope. Yes. And that's why we decided for using the series circuit in our case.
So simply because of the fact that it was easier for you to measure it.
And we have the better accuracy on the measurements of the voltage in our setup.
Yes, actually, but...
And the currents also flowing in our setup are really low. It's like milliamps. So it also would be really hard to measure.
Okay, and you were not varying it. Okay.
We were not varying.
Okay, thank you so much. Well, I actually think that for the parallel connection, we may have some higher efficiency, for example, for the calculation, which may compensate this disadvantage of the experimental setup. However, let's move on to the next question.
But how would you think the parallel setup and measure?
It may be like that. It depends on your experimental setup and in general everything else. So like I cannot judge. I think that it just simply must have been checked since it's one of the parameters of in general this task. So let's move on to the next question. And actually you are like let's talk about a little bit more on the small amplitudes approximation. So like can you talk more on it? Like were you like because I didn't receive any like so clear answer about that.
Using the small amplitudes approximation, I think you are want to mention that we don't investigate the hysteresis of our problem.
Yes.
So in fact the 37. Okay, so here we can see the values of the magnetic field inside our coil for the measurements that we did, for example. And we can see that those values of the magnetic field intensity are around up to 14 amperes per meter. And we can see when we compare the hysteresis, for example, for the material X0, which is really close to our ferrite core that we used, we can see that the values of the magnetic field that they use are over 100 times higher than the ones that we use. And in fact, our hysteresis loop for the range of the measurements that we had will look just like the straight line. So it wouldn't affect our results significantly. Okay. We also chose this range to obtain the most basic magnetic properties of our rods and not investigate other nonlinear effects because they can cause the we also have to take into consideration other coefficients, which are also with some certain uncertainty, yes, and this will also affect the accuracy of our measurements.
Yeah, and can you just briefly explain what is in general the reason why we observe this hysteresis in general?
Why we observe the hysteresis in general? So it is the fact due to the fact that the core has to magnetize and demagnetize, and when it happens really fast, those magnetization will also take some energy to magnetize and demagnetize, and yes, the energy will dissipate as the heat inside our yes, ferromagnetic yes, material.
Thank you so much. I have a minute to sum up this discussion. So I'm very grateful for this discussion. It actually indeed was very fruitful for us. So at first we were able to look deeply in the optimization of this problem. So we were able to see that the reporter actually was optimizing the capacity and also the values of the rods in their system. However, unfortunately, I again must mention that I lacked the investigation of the optimization of the frequency and some other parameters in this case. We were also discussing the case of the losses in the system and came to the summary that the main reason of the losses was actually the skin effect in the solution of the reporter, and they have taken it into account, again, a great advantage of it. We also discussed the hysteresis, which I think is a very important case, and I appreciate the reporter for investigation of it and for the proving that it is actually not applicable for their case. Here it is visible that they do not take it into account because it wasn't playing a significant role. And we also discussed the nonlinear effects and how they may result in this task. So thank you for your time.
So the first question is for overview that what is the role of permeability in a circuit? Is it inductance or resistance?
What's the role of the magnetic permeability in our circuit?
Yeah.
So it increases the...
Is it inductance or resistance?
It increases the inductance or the resistance? It increases the inductance of our coil.
So inductance, okay. So
yeah, I agree with it, of course, inductance.
Okay, so for reporter,
we showed that it's in the inductance and is affected
I
by both the conductivity
so
and
which
the
electric component do it has?
Which
electric component do it has? Resistor or inductor?
What?
Which electric component do it has?
We measured the by fitting the curvature and using our analytical formula for the inductance of our coil, we're able to
test inductance. Okay.
Yeah, so we're fitting the inductance.
So
as I showed, the inductance creates the imaginary part of the inductance creates this non-contact resistance.
Okay, so have you considered quality factor of your resonant frequency? Quality factor.
What factor?
Oh, okay, do opponents think the quality factor of the resonant frequency is important?
Well, yes.
Okay, so why not you choose to use parallel circuit?
As I said before, we were able to measure the voltage more accurately than the currents, which were really small in our circuit.
So next question, have you calculated the skin depth of your rod?
Have we calculated the skin depth? We didn't calculate the skin depth. However, it is the result of our Maxwell's equations, as we showed here.
Okay, so if your rod completely fell in your coil.
Yeah. So it wasn't completely fixed? No, it wasn't completely fixed. We had a plastic form into which we inserted our rod.
Okay, so the opponent think that filling factor of the coil is important. Filling factor.
Well, I probably it may result for some of the parameters.
Okay.
I mean, as all the factors, it depends on the parameters.
I think here is also filling factor that we can see.
So have you considered time domain, the method?
Time domain?
Yes, because you're now using frequency domain. Have you considered time domain for better accuracy?
But I think the frequency domain and time domain are
opponents think that will be another method.
In general, the investigation of domains is very interesting. However, it's very complicated, so I wouldn't expect it to be investigated as like in
I think that the frequency domain gives us more information about the curvature.
Okay, so can you turn to page 29?
What?
Page 29.
29. Yeah.
So can you explain the reason of deviation on the top?
On top?
Oh, like the quality factor, like the width at the maximum height. Yeah.
The frequency it can be really precisely measured because we know the value from the wave generator, and it works pretty exact. So
okay, thank you.
I don't understand the question too much.
Of the reviewer, but we will let them try to connect to the projector or TV. Did you test the computer beforehand? Yeah. So did you break it, guys? Just to making it hard for them. Oh, okay. It looks like okay. Okay, please.
Okay, so I'm a reviewer from Team Taiwan, and we are reviewing problem 6, non-contact resistance. So, review of the report. For observation part, that the effect of the rod is shown in the experiment video, and I think it is easy to understand, and he has do some preliminary measurement. However, I think that the graph of it is not very unclear, and I think the parallel LRC setup should also be considered. For the theory part, the reporter also used the resonance and considers the gain effect of it, and I think he considered the limit of the measurement and then considered the energy dissipation, which is very important. However, I think he missed the proximity effect. When the two conductor is close, that proximity effect will come out, and this is very important. So, and he didn't consider filling factor and the damping motion of the LRC circuit. For experiment part, he drew a parameter about radiant material and driving frequency. And I think all of this parameter is important. However, I think he didn't consider the quality factor of his resonant frequency. So for data analysis, he do the conductivity and permeability. However, I think the time domain and internal LC is what we'll call a deviation. And for opposition, that's you clarify the problem. However, I think like some of the question is not comprehensive and very imprecise, and the optimization is not very related to the problem statement. So I think it wastes too much time on the optimization. And for the discussion, they talk about skin depth, number of coil, limit of Maxwell equation, and other properties of ferromagnetic and rod and non-magnetic rod. So here's the key discussion they have talked about. So the opponents think that hysteresis is very important. It needs to be considered. However, I think that it should be negligible because in high frequency, there will be demagnetization will occur. So I think that hysteresis is negligible. And for the opponent asks about the skin effect, and we calculate the skin depth of the reported setup, that it is actually quite big compared to a radius. So I think the deviation could be calculated by considering it. And here's our question: the permeability perform as an inductance because it is related to the magnetic flux density. And also, the conductivity performs as resistance because it is related to the current flow in the inductance. So, and finally, we talk about the parallel LRC circuit and a series LRC circuit. So I think the main reason why it didn't use a parallel LRC circuit is because quality factor. The quality factor is very important for we examine how the resonance is good or bad. So we think that the main reason why don't use a parallel factor is the quality factor will be very bad. So also the missing point is about the filling factor. So because if the rod didn't completely fill in the coil, that needed, I think the reporter should include this, and for creating a more general formula for different size of the rod inside this inside his formula. And also, I think that the proximity effect is different from the skin effect because, and this will also cause a large the deviation that they needed to consider, and the reason of this effect is different. So yeah, I think the opponent should also discuss it in the discussion part. Thank you.
So first, I would like to start with the nonlinearities which were discussed. So we had the region for which we can see that our fitted functions fit really well, and we can see the nonlinearities are really negligible, as we can see, for example, on this graph. Then there was questions about the range of the frequencies that we use. So we used the range of the frequencies for which our oscilloscope was really had satisfactory accuracy, and we also for which there are the nonlinear effects are negligible. We used series circuit because there were questions about the parallel connection. So the problem content requires us to propose a method for our measurements, and we did from all we had. We had the oscilloscope, which was able to measure the value, the voltage really accurately for high frequencies such as this, and the regular multimeters don't work accurately for such a high range of frequencies that we investigated in our problem. And that's why we wanted to use the series connection. There were questions about the time domain, so I think the reviewer wanted to see the sign function differences for different rods inserted into our rod. However, all of these points are made out of the graphs from the time domains, because we had to fit the had to get the amplitude of the oscillations for each of the frequencies, and then we applied them to our curve, and we obtained the resonance curve for which we fitted the values of conductivity and relative magnetic permeability. There were questions about also the skin depth, which we analyzed analytically, and we had the exact analytical solution and the distribution of the magnetic field inside our rods, which we investigated. So, and the last questions were about the filling factor. So we used 34. Okay, so we use different radius of the rods. Okay, sorry for this.
Thank you very much for respecting it. That said, like finishing the sentence. Okay, thank you very much. Let's have an applause for all the reporter, opponent, reviewer. And can I ask the opponent and reviewer to join the reporter on the stage for the questions from the jury members? And yeah, jury members, you are welcome to pose questions. Could you? There are 2 microphones circulating here around. So here you have one.
Okay, so I guess I can have a question. So on slide 33, can you go there? Do I understand here this graph that you have only one correct point with relative accuracy of 1, and almost all of the others relative accuracy 0 means that it is not an accurate measurement?
It's the relative accuracy, so it's the difference divided by the value of the accuracy from our independent measurement.
So the relative accuracy of 0
so
is
if
a
the
good
accuracy
measurement.
is relative accuracy is 0, it means that it's very accurate. So it's a deviation.
Okay,
sorry.
thank you.
Yeah.
Okay, Georgi.
Hello. So my question is, during the discussion, I also heard similar things. When we have alternating current, and what happens, can magnetization change, or can there be some hysteresis or something like that?
So
is the problem
as
I want to
we had really low values of the magnetic field inside our in slide number 40, I think. Yes, so we had very small values of the magnetic field inside our coil, and for which the hysteresis, which will be negligible, as we can see here. The values of the magnetic field would be required to be 100 times higher for the hysteresis loop to be observed. And however, also
okay, thank you very much. We have to continue.
Is the effect for
I'm sorry.
Okay.
Please.
Yeah. So a question to the reporter. I saw in your picture that the radius of the
continue.
Okay. That the radius of that driving coil is relatively large compared to its length. So I was wondering, how did you treat the effect of the fringe field of that coil?
You mean the losses at the top and at the bottoms? Yeah.
Yeah,
so our model we only investigated this. We use only the solenoid approximations, and we didn't investigate these losses, and we approximated that they are not so significant.
Okay, Eric?
I had the exact same question, but did you then experimentally verify?
So you can have a follow-up.
Did you experimentally verify the spatial distribution of the magnetic field?
What distribution?
Of the coil.
Outside the coil, you mean? Or
so did you experimentally verify that the effect is small, that given
yes,
the size of your coil?
I think it's because of our functions fit really well the measurements. Whether I can say this. Yes. So
okay.
That's the reason how we explain this.
Yeah, please, Patrick. We have to move on. Sorry, guys.
I would have a question to the reviewer. You have mentioned in your questions and also in your speech that he has only worked in frequency domain and not in the time domain. Why would you think this is important?
I think this is like an alternative method.
Okay.
So in his observation, he has mentioned about his use impulse on that, and he showed us the decay of the current. So I think that by measuring for the envelope of the current, we can get direct, like the damping factor of this circuit, and we can get through inductance from it and directly. So this is an important factor that can be investigated in the phenomenon.
Okay, thank you, Claire.
Yeah,
do your conductivity and the permeability frequency dependent, or just it's a single value for the whole frequency? What did you fit to?
So we assume that the conductivity isn't the frequency dependent, whether it's not. The conductivity of rods, it's not frequency dependent, because it's this effect also will be negligible in the range of the frequency.
On, I believe it's the slide number 32. Yeah, so especially for the stainless steel, it looks like the errors are like orders of magnitude. So you said you didn't optimize, but like, is that for you like a satisfactory result, producing something which is like deviates there and back like more than a factor of 10?
Okay, so here's also the relative accuracy, and here's the relative errors of our measurements.
No, but like if you can come back on 32,
okay,
then the green lights then spread like some of them spread to from 5 times 10 to the power of 6 to I don't know 10 to the power of 4 and less. So certainly that's more than a factor of 100.
Yeah, but it's also the fact that the stainless steel is really poor ferromagnetic material, and it is a poor conductor, and that's why these values are significantly lower than the rest, and this is the problems with the accuracy of the this method.
Okay, okay. Thank you very much. I'm sorry, we have many jurors and little time, so I keep it in my head about the jurors they didn't manage to ask this time for the next round. Thank you very much, guys, for your answers, and now it's the task for the jury to put the grades. While, yeah, you can give an applause. Thank you. Please, again, while the jurors are working, including myself, keep calm. I know you would like to discuss everything. Give us a few more minutes to do our job, and then use the break for the discussions, because it's very hard for the jurors to concentrate if the whole audience is buzzing around. I also want to comment, so I'll go in there and check the jurors. If I interact with them, it's not that I am saying them what they should and how they should grade, but statistically, the chance of not summing correctly, it's almost at least 1 for this number of jurors. So if I see a mistake in the calculation, then I tend to correct the juror so that you don't have to check the score sheets afterwards. Everyone is checking now. juror writing down their grade into the scoring sheet, so you can tune. How exactly do you sum here? It's 1, it's 5, 7.5 minus something must be 7.5 minus. But like, how can you 7.2? How can you round up 7.3? I can't. You shouldn't. Okay, ready? Ukażesz ty. Nie. Tak, ukaż myszko, no to daj. Okay, so please, the jury members, show us the grade for the report. Now, I'll start reading from the back end of the jury. And it's a 7, 8, 5, 8, 6, 7, 7, 7, 6, 5. That's for the report. For the opponent, now it's a 7, 7, 7, 8, 8, 8, 9, 7, 5, 8. And for the review, now it's a 6, 6, 3, 5, 6, 8, 7, 7, 6, 5. Thank you very much. I'd say it's a rather unusual spread for the finals. But anyway, okay, the report was, yeah, kind of okay. Maybe Patrick, would you comment on your 5?
I think that what you have done was quite good. I was missing some things, like what he mentioned, the optimization. Then also the plot where you have shown your final measurements, and we could see that it has 2 orders of magnitude. You cannot just show that it has 2 orders of magnitude and then not say anything about it, that, yeah, it's a correct measurement. So I was kind of missing these things. And then in the discussion with the opponent, I also felt that it wasn't that good of a discussion. So for finally, I gave 3.5 for the report, 1.5 for the discussion, and then -1 for the answers to the questions. And I came up with a 5.
Okay, thank you. I was also on the 5 side. Yeah, basically we met with the same problem a few days ago. It was a 6 at that time, but I think now the opponent made a better job in showing the discrepancies in the report. And from my point of view, basically I echo what Patrick said. Like. You can't say the optimization is not the task here, and at the same time ending up with a device which gives you like a factor of 10 plus minus results. So from my point of view, this is not a satisfactory. So I had half of a point more, so 5.5, but I finally rounded it down. But let's say Anna for the 8.
Yeah, so I think it was a really great presentation. I liked all the explanations behind it. Like I think it was very easy to follow with your reasoning. What did I write down? Yeah, I also like that you discussed really the limits of your theory. Like for example, how you included the rod diameter in this theory and why it doesn't fit on the one side and why it doesn't fit on the other side. So I was very happy with this.
Okay, thank you very much. For the opponent, we had a single rather low grade by Claire, so that was a 5.
Okay, I can see that opponents trying really hard to get a hold on the good discussions, but some of the questions not much interested in the real problem task and what they did. And one thing that interests me is something about the efficiency and the optimization. They spend quite a lot of time on discussing that, but I'm still puzzled about what they mean by efficiency and the optimization. Is it about the task? Is it about the measurement? Is it about the overall problem solving? I wasn't clear about what they mean by why they are even discussing it, and I was kind of lost what they are discussing about.
Okay, thank you. But Sergey, you were almost on the top. No, Sergey.
Yeah. So I think for me this discussion made the most important points, especially for limitations of the model, because the model was presented rather well. But then it wasn't discussed if there are any limitations to this model, and I thought the opponent brought this up very well. Plus, I very much valued that the reporter, the opponent was willing to concede any good points made by the reporter and accept that some things might have been done for a purpose and with a reason. And that's also part of the good discussion, because the point is to make the thing as strong as possible, the report. Plus, I gave good points for the summary of the report, which I thought was done very well.
Yeah, okay, thank you very much. We don't have much time, so we proceed to the reviewer. If there are any other comments, please feel free to discuss during the break. Yeah, reviewer, Patrick, a 3.
So I would first say my partial grades and then clarify why I have given them. For the questions, I gave a 0. For the review of the report, a 1. Review of the opposition, 0.5. For the discussion analysis, a 1. And then minus 0.5 for the answers to the jury questions. And basically for the questions, I think you have asked totally irrelevant questions, and you didn't really ask what happened during the opposition, clarifying things. I would have expected some questions in those terms. For the review of the report, I have it written here, and your terms that there were written like hidden important parameters, clear physics ideas. I don't want to see very general terms. I want to see what is happening exactly, and you need to write what was going on. Then for the reviewer position, same, that you have written that she has asked imprecise questions in the short questions, why I think that her questions was one of the best part of her opposition. And also you have mentioned that the optimization is not relevant, why the optimization is not relevant, why the task clearly says that you need to be able to measure the properties. And I think that's one of the most important things in this task. So because I disagree with you, I gave a low points there too.
Okay, thank you very much. But still, we had an upper end as well with Vitaya.
I think the reviewer gave efficient pros and cons of the report and the opposition. And I particularly like when you introduce a concept like quality factor. Whenever you see resonance curve like this, it's very difficult to ignore the quality factor that you mentioned, and also the filling factor that you try to discuss with the other teams. I think that's a very interesting concept. Thank you.
Okay, thank you very much. Just a technical comment, and I think it's very important for all the participants as well on the jurors. There is a big difference between the opponent and the reviewer, and the reviewer is basically asked to review what did happen before. So you are strongly discouraged, unless it's extremely important to bring new concepts and topics, etc., into the game. So I was not on the extreme, but I have to say that like I felt like your review was more in a opposition way, you know, bringing new ideas, new concepts into a presentation which was full of interesting ideas and full of interesting concepts, and that's why it was nice in some sense, but technically it did not really match what we expect from a perfect review, like from my point of view. Okay, thank you very much. Let's have a 10 minutes break, but please, I know we are a lot of us who want to get drinks, etc., but please try to be efficient, and let's gather here in 10 minutes if possible. We have the team from Ukraine reporting, team from Taiwan opposing Chinese Taipei, and the team from Singapore reviewing. And I just pass the clock to you for starting the 5 minutes preparation. Whenever you are ready, even earlier, please let us know when we can start.
One, two, three.
1, 2, 3. 1, 2, 3.
Yeah, great. Thank you so much.
Я только потом увидел, что он логарифмический вообще погрешность. Так он сказал логарифмическая. Да, но все равно 10 шестой, 10 четвертая погрешность. Как ты? Сейчас, у нас будет проблема. Я не думаю, это вообще такое ставить презентацию.
Не знаю, подержи.
Это вообще, ну, стирается, да.
Все, скажешь? Сонечка, как мы говорим?
Уверенно?
Не, давай. 3 фактора. И полный рот. Полный рот. Полностью все мышцы, как будто мы нам рассказываем. Еще не забывай улыбаться. У тебя тут целая аудитория перед тобой. Тебе надо заявить про себя. Первый репорт должен быть прям. Окей?
Особенно после такого фейла от поляков.
Да.
Соня, не обсуждай все. Я тебе мотивацию дал. Все понимаешь?
Все, давай, рыбка.
Так.
Ставь на начальный слайд.
Да.
Готово?
Так, смотри, вот здесь слайды твои, да? Все, так. Что, пультик? Вот. Не проверяй.
Все, давай, удачи. Когда будешь готова, начинай. Можешь сейчас.
А они сразу включат время?
Да. Ты смотри на время обязательно.
Вы мне показали.
Ну я же не знаю твою презентацию, я не знаю, когда это там заканчивается. Все нормально будет, мы тебе хорошо расскажем. Да.
Okay, so hello, my name is Sofia Fedoskina. Today I will report the task number 15, wet scroll from Team Ukraine. So in this task, we should gently place a piece of tracing paper on water surface. Then you trap the cursor into a scroll and slowly uncurse. we should explain and investigate this phenomenon. So now you can see the demonstration of this effect, which we divided into 3 stages, where the first stage is rapid curling of the scroll, the second stage is unscrolling of the scroll, and third stage, it is interesting effect, the scrolling and unscrolling after that several times. So we divided the first stage into 2 substages. So where the first substage is forming of the curls in both sides of the sheet, and second substage is when these curls are moving towards each other. So it is very important that we saw in our experiments that the radius of the curls don't depend on time, which we proved by doing tracker, where we could see that the radius is constant in time. So let's qualitatively explain this effect. So when the paper is absorbing water, the lower layer is expanded firstly. That's why the paper starts to twist. But it is important effect that in our experiment we saw that paper sheet is curling in one specific direction, which happened because the paper sheet is anisotropic. So we qualitatively explain this effect. But there are also further scrolling, so the friction forces are clutching and the scroll is rolling up. We divided our next problem into 2 separate parts, where the first problem is the problem of swelling, and the second is the formation of the scroll. So now we can move on to the swelling problem. So there are different mechanisms of swelling and different papers. So for common paper, it is imbibition mechanism that is lifting water by the capillaries. And for tracing paper, it is molecular diffusion mechanism, which is happened because the tracing paper is filling by gel. So that's why we characterize the water content in the point of the paper as the ratio between mass of water that paper absorbed and maximum mass of water that can be absorbed by the paper. And then we wrote the diffusion equation and proper initial and boundary condition, where the expression in the gaps is water flow z-axis. And which is important, we wrote our model equation for the diffusion coefficient, which takes into account saturation of water layers. So we solve this equation and obtain from it water content. So we introduce the z-axis and the free deformation, which is the deformation of whole paper layer on which other paper layers are not contact of which are paper layer. So it is in our model proportional to the water content. And also we found the factual deformation of paper bending, which is the deformation of paper layer on which other paper layers are contacting. And it is determined by the radius of the scroll and location of neutral layer. So then, we determine the stress in each layer by the difference of factual and free deformations. So we previously obtained the diffusion equation and the stress. And now we wrote the force balance equation on this paper layer and also equilibrium of torques. So from these equations, we define the location of neutral layer, the 0, and which is important, the curvature of the sheet in each moment of time. So there are 2 coefficients, the 0 and alpha, that are unknown yet, but we will show how we obtained it in our further presentation. So in order to do that, we did the experiment where we used the lightning behind to obtain the contrast photos and directing threads for fixing location of the strip, otherwise it is sleeping, and also obtained the photos of the profile. So we did this procedure for consistent moments of time and obtained the dependence of curvature in time. So now you can see the 3 examples of the scroll form from which we obtained the radius for each frame and build this curve. This is our experimental data, and we can qualitatively explain it by I compared it of plot of distribution of water content in z coordinate, where each curve is made by doing different moments of time. So we can see that where there is more time, the curve is more straight, which actually explains qualitatively the position of these experimental dots. So then, we solve the system for the water content in that coordinate, free expansion from that coordinate, factual expansion from that coordinate, and also tension. And which is important, we found the curvature of the sheet. So now we can build our theoretical approximation by our theory and feed by this curve parameters d0 and alpha for this tracing paper. But also we have the baking paper, which actually is similar to tracing paper, but has different structure. That's why we have the different parameters d0 and alpha for these curves. So we fully investigated the problem of swelling, and now we can investigate the problem of the scroll formation. So we introduced the s-axis and axis zeta and xi, and watch the forces that are acting on the small piece of the paper. So we wrote the balance force equation, where we wrote the two tension forces, pressure force and gravity force, and also expressions for it. Then we wrote the relations between coordinates and projected in coordinate axis. Then we wrote the equilibrium equation, and which includes the tension forces talk and projections on tension force talk. So it is our full system of equations and unknown functions. And now, and then we wrote the boundary conditions, which are including the force balance on the edge, torque balance on the edge, and free boundary condition and sheet symmetry. And from these equations, we define the scroll form till untouching moment. So it is important, as we said, that the radius of the curve don't depend on time. That's why the radius of the scroll depends on the moment of time when the water is detaching. So we wrote the equilibrium equation for the meniscus and then defined the radius of the scroll. So then we plotted the parameter surface tension. So we investigated the scroll radius from surface tension. And we saw that when the surface tension increases, the scroll radius increases too, which is very important parameter. So then we can investigate the velocity of scrolling. So we wrote the equilibrium equation of torques and wrote the expressions for the tension forces torque, surface tension torque, pressure torque, and dissipation torque. And from this equation, we define the velocity of scrolling. So now we can investigate it experimentally. To do that, we did the experiment where in our experimental setup, we use the paper which is fixing in one side and let it down until reaching contact with water. And the paper starts to scroll in one side. So we explore the dependence of rolling velocity in time, where we can see our experimental dots and theoretical approximation for tracing and baking papers, which are different, as we said, because they have another structure. So then we investigated the parameter which depends on velocity, which is the paper sheet width. And we can see that our theory didn't consider it, but when we did the experiment, we saw that when the paper is approximately till 2 centimeters, the scroll is not scrolling. Well, from 2 till 4 centimeters, approximately the scrolling velocity is low, which happened because the meniscus along sheet sides are decreasing velocity of scrolling. And we can see that when the sheet is greater than 4 centimeter width, the scroll moves with expected velocity. So we fully investigated the first stage, but we didn't investigate the second and third stage, which we'll investigate now. So we wrote the same equations for it, but another initial and boundary conditions. Solve it the same and obtain the dependence of scroll radius from time for unscrolling. That is our tracking that we made, as we can see in the photo, and the experimental curve. that we made by this theory. And we can see that it is deviations from this experimental dots and theory. Now you can see this plot bigger. And this happens because there is the slipstick effect. And the paper, when it is unscrolling, it is slipping. Then we can plot a curvature from time where we can see the scrolling and unscrolling. So that is deviation in the scrolling. Because our theory didn't consider the vanishing of the curvature. But it is the great result because it is very complicated to do. So then we investigated the further scrolling of the scroll, which is very important, and we can plot the further scrolling of the scroll, but the further scrolling of the scroll is unpredictable, and also there is no particular point to track the curvature because there is no the arc, the form. So we fully investigated the second and third stages. So in our preliminary part, we demonstrated the effect and qualitatively explained it. In our second part, we showed our swelling model and solved the system. So in our third part, we solved the system for the scroll formation and investigated major parameters. Also, we investigated the second and third stage. So, and also we investigated such effect as slipstick, which is the deviation. So, thank you for attention, and here is my literature.
Okay, so first question. Do you measure the Young's modulus of paper by yourself?
Yes, of course, we measured the Young's
okay,
model.
Thank you. So, and do you measure the paper strain by yourself because the water expands after? So
we don't have such a parameter, paper shrink, in our theory.
So you do not measure the expansion of paper after it's.
We measure the expansion. It is our beta coefficient, the expansion.
Okay, so do you measure your the thickness of your paper?
Yes, we measured it by our microscope.
You mentioned that
micrometer.
Okay, thank you. You mentioned that there is a particular fiber orientation in your paper. Did you measure it?
Particular fiber. What do you mean by?
Like you mentioned in your PowerPoint that there are two particular directions: machine direction and cross direction.
Ah, yes. It is because the paper is anisotropic. Yes.
Yes. So what causes the anisotropy? Is it because the fiber orientation?
No, it is just because the structure of the paper. It is
okay, thank you. Do you put the tracing paper on the water surface by hand?
Yes, but we put it very gently, so it is. We try to do it's homogeneous.
Okay, thank you. And you mentioned you use tracing paper and baking paper for this phenomenon. What is their difference? Is the difference because of porosity difference?
Yes, it is difference in the coefficients, D naught, alpha, beta, and other coefficients.
Okay.
It is the structure of the paper.
Then do you measure those coefficients independently for both papers?
Yes, we measured this coefficient for the both papers.
Okay. Do you consider evaporation in your phenomenon?
No, it is negligible effect.
Okay. In page 12, you showed your setup. Do you consider the effect of nylon string?
What? In page 12? Okay. Умничка, смотри, что он имел в виду. Он говорит...
So, good morning. I'm Team Taiwan. Today I'm going to oppose problem number 15, wet scroll. So the problem states that we should gently place a piece of tracing paper on the surface of water. It rapidly curls into a scroll and then slowly uncurls. Explain and investigate this phenomenon. So I think the key questions here, firstly, we need to study the possible curling motion of the paper and why we need a tracing paper, particularly for this phenomenon. The significance of it is quite important. And the problem mentions that it rapidly curls and slowly uncurls, so we need to study the uncurling and curling speed difference. For the report overview, briefly, she observed the curling and uncurling phase, and she observed that in a particular phase, the radii is not time dependent, and she mentioned that the diffusion is the main mechanism of water penetration, and water content is the main factor that causes the paper to curl. And she defined curling as non-zero curvature, and she also used baking paper for this experiment. And she measured curvature by video tracking, but that causes a problem about the transition between no scroll and touching of each other. And also the boundary, the possible curling motions are not at all mentioned, and the significance and effect of setup, that is quite important because she used nylon string for this phenomenon. And for the curling mechanism, she defined the water content as volume ratio and assumed the water penetration is driven by Fick's law. And measurement and she said she measured the Young's modulus of paper strain, and but she did not mention pore size. And okay, and she also imposed boundary condition on Fick's law, which I'll discuss later. And for the direction, she mentioned that the water has an anisotropy, but she did not mention the cause of it. And I think it's because of fiber orientation. And she concluded that water content dominates curvature. And I think that I think that has a quasi-static assumption here. For the baking paper, she does the she think that probably it has some dependence on porosity, and for the width, she observed that width of the paper affects peak time and curvature, and the rolling and the drag, like things like that. And okay, and for surface tension, she mentioned that surface tension can also affect this phenomenon by affecting the previous phase. Okay, so for discussion points that okay. Firstly, the possible curling motion need to be discussed. Like the measurement of curvature when multiple cylinders is involved. That is like when the paper actually gradually curls up. It is not a full cylinder. It consists of two. So when this is involved, the method she used, fitting a single circle around the tracing paper, is not accurate. And secondly, she only described the case where the tracing paper touches each other, the ends touch each other. But there are other curling motions which she did not discuss, and even the sinking of tracing paper is not mentioned. And also for water penetration, she mentioned that the diffusion is the main mechanism, but she did not consider evaporation, which is a crucial point to this phenomenon. And for the curvature dependence on time, okay, she did not observe the existence of finite curvature, and she also states that the curling motion after a particular point is totally like unpredictable, and I disagree with that. I'll discuss with the reporter about this. I'll invite the reporter to the stage. Okay, so firstly, some clarifying questions. Like, continuing from the short question, can you switch to page 12? Like,
yes, here it is.
Yeah, you mentioned that there is a where's my laser point? Oh, you mentioned that you use strings to confine the paper, right? Or to support the paper.
Yes, we use the direction threads for fixed location of the strip, because the paper is slipping on water, like it is moving.
Yes.
And we fixed it.
Okay.
To measure it accurately.
Do you consider that the string will also affect the curling and uncurling stage of this phenomenon?
Yes, but it will be negligible effect. It's like not very affect this effect.
I think that I disagree with you because you mentioned that the meniscus between the paper and the water is important for this phenomenon. You just mentioned that, right?
But the directional threads don't touch the meniscus.
You mean sorry? You mean
they're like a little. They're not touching. They're not like pulling the water.
So the string.
They are like gently touching the water, just to make it not moving.
So the string touches the water, but they do not form a meniscus. Do you mean like that?
No, I mean just these threads are not effect. The threads are just gently
okay,
like.
Thank you. And also, you said you put the tracing paper very gently by hand. Can you show me how you do it? Do you have a video for it?
No, I don't have a video for it, but I think we just.
You put it just gently.
Yes, we put it just gently.
Do you ensure that the initial curvature of the paper is 0?
Yes.
How so you tracked it from the start okay.
No, it is obvious that the curvature is 0 in the initially.
I disagree with you because if you put the paper gently means that the velocity is quite small, and because of that the time above the water surface is really large. But the water will evaporate, and the evaporated water will go into the paper, causing non-zero
evaporation
curvature.
is very negligible effect in this case, because it's very small time when we place it, and it is small time like for scrolling, and evaporation it's like a negligible effect.
Do you observe all the papers are do all the papers uncurl completely to 0 curvature? Do you observe that?
Like in our experiment, they are unscrolling till yes, till.
Can you switch to the data you mentioned that the time evolution of your curvature?
Do you mean the plot this?
Yeah. Do all the papers uncurl to the 0 curvature? Do all of them?
Like it's very small. It can be like nearly 0.
Okay.
Zero.
But you mentioned that some of the papers will curl again in the.
All nearly all papers will curl again.
And I think it
depends on the properties of the paper.
I disagree with you because I think that the evaporation plays a role here, because the evaporation causes the water content on the top layer to decrease, and the water content in the bottom layer remains a constant because it's constantly supplying. So that results in the final curling.
No, as I said, in our opinion, the evaporation is very negligible effect here because it's very small and time is very small. It's not. It will not affect.
Okay. Okay. You also mentioned that the primary driving force of water is by diffusion. Am I correct?
What do you mean driving force? Like scrolling?
The water penetration into the paper.
Okay, yes, it's the diffusion.
It is by diffusion. So you agree,
yes.
So do you agree that by using this you're actually using the random thermal motion of water? Because you used Fick's law, right?
No, we use the diffusion equation.
Okay, that is another name for Fick's law. Sorry for that. So you use diffusion equation, and diffusion equation. The diffusion coefficient is actually related to the minimal. It's actually related to the mean free path of the particle. So it is related to random thermal motion, or also known as the Brownian motion. Do you agree with me?
We just wrote the diffusion equation because the tracing paper. Yes.
So okay, sorry. So diffusion is by using the diffusion equation, you're actually assuming that the water molecules are moving like under random thermal motion, and this causes the penetration, right? Okay.
Yes,
and
the water is penetrating between the molecules of the paper.
okay, but you haven't considered capillary effects here. You mentioned in your like phenomenon description, like
No, it is not the capillary effect because the lifting by the capillaries, it is the effect that is absorbed on usual printing paper. We saw in the literature that the
can you prove that capillary can play a role in this phenomenon, like tracing paper? Can you prove that? Do you change the surface tension of water? Like, do you do any experiment on that?
Yes,
Can you show me the data, if you have done it?
It was in the presentation even. I try to find.
If you can't find it, that doesn't.
No. I will find. Yes, here it is.
Okay, so you change the okay. So you're actually saying that surface tension plays a role in this phenomenon. So why do you say that surface tension is not relevant?
I didn't say the surface tension is not relevant. I just said that it is not the lifting water by the capillaries.
Okay.
I said that it is diffusion mechanism.
Okay, I understand. But I think that the diffusion actually has a definition. Like in actual definitions of diffusion, we actually need a common solvent to do this. But in here, we only have the water and the fiber. So I think we don't have a common solvent. So I think that diffusion cannot apply. We should use capillary suction for this model.
No, we even took it from literature. There is the paper where is written that from tracing papers, that is mechanism of diffusion. I even can show.
Okay, thank you. I've read that paper before, and like.
What?
Okay, okay, let's go on to the next topic. Like, okay, there are like you mentioned that the tracing paper actually curls again, right?
Yes.
Yeah.
Yes.
And I think that effect, apart from evaporation, I think that can also be explained by.
No, it is not about evaporation. I even.
Then how do you explain it then?
Okay. So it is scrolling because the water content is distributed by the thickness, and there is more free place of water to diffuse, and water starts to diffuse again in these free places that went up to
Can you show me the data, like when
What
it curls
data?
again? When it curls again, do you have any data? Like you said, it's unpredictable, but like. I think that
I even show it like.
I think that the problem might come from that you imposed boundary conditions on the bottom side of the paper that the water content is saturated, right? The diffusion equation, the bottom layer is saturated.
I should explain boundary conditions, or
you impose the boundary condition that bottom layer is saturated, right?
Yes.
Okay, but I think that when the paper is actually curled up, then the curling part does not accept water from the bottom. So in this case, the boundary condition is not.
We changed our boundary conditions.
Okay, thank you very much. Discussion is over. You have 5 minutes to
Okay,
summary the discussion.
So for a summary of the discussion, I think that the string, because she used the string to confine the paper in a position, but the reporter neglected all of its relevant effects, and I think that is not negligible. And the initial curvature is she think that is always 0, but I think not, because when the paper is placed gently, water will also diffuse into the paper by vapor. So I think that the initial curvature may be not 0. We need to ensure that. And final curvature is caused by evaporation. She did not consider evaporation at all in her
theory. And for the mechanism, she think that this effect is caused all by random thermal motion. But I think that the equation she used does not fit the scenario, does not fit the diffusion definition. So I think it should not be used. And the surface tension, she said, it is relevant to the phenomenon.
To the reporter, do you account for the curling in the machine direction? So I noticed you accounted for curling in one direction, correct? Do you account for curling in both directions, or do you assume only one direction?
Do you mean cut the
Yeah. So do you account for the curling in both directions or just one direction?
I don't
it's all right.
understand the
To the
question.
opponent, do you believe that the paper expands in only one direction?
No, the paper expands in all directions.
Okay, thank you. To the reporter, do you calculate your capillary number?
No.
Do you have an order of magnitude estimate for the speed of the waterfront?
What?
It's all right. To the opponent, do you think that capillary action is significant?
Yes, of course.
To the reporter, do you account for the change in the weight of the water, in the weight of the
Yes.
paper as it absorbs water?
Yes, we changed the width of paper.
Sorry, the weight of the paper as it absorbs water. Do you account for this?
The width of the paper, yes, we changed.
So the weight of the paper increases as it absorbs water?
Yes, yes.
I see, all right. How did you ensure that the paper was dry before the experiment?
Can you repeat, please?
How did you ensure that the paper was dry before conducting the experiment?
It wasn't dry.
Oh, I see, thank you.
It was, how do...
How did you ensure that the paper was dry before the experiment?
It shouldn't be that it is
I
dry.
see. May I ask?
It should be dry.
I see, thank you. May I ask how many free parameters you have within your theory?
What do you mean by free parameters?
How many?
That we don't measure it.
How many of those did you adjust to your experiment?
3.
I see, thank you. To the opponent, do you believe that evaporation is significant?
Yes, of course.
All right, thank you. Could we go to slide 9, please? May I ask what alpha is?
Okay, so alpha, it is coefficient of the difference between paper surfaces. So if we place, if we rotate the paper in, if we put the paper in this, like this,
it's all right. In the interest of
another.
time, I'd like to move on to my next question. Could we go to slide 31, please? Are the dotted lines your theory? And if so, what are the solid lines in this graph? Just briefly explain, please. Like, is the solid lines an approximation?
It is our approximation by our theory.
So you're solving your theory to get the green line?
Yes.
I see, thank you. To the reporter, do you use the same Young's modulus for both wet and dry paper?
We use dry paper to put it in on the water.
It's all right. To the opponent, do you believe that sinking has a significant effect? Yes, just yes or no, please.
Yes.
Do you have a brief explanation for why you believe the paper curls a second time?
Because she mentioned that surface tension will pull the paper, but if the surface tension is not enough, it will sink.
Sorry, why do you think the paper curls a second time? Oh, it's all right. Thank you. Test. Oh, hello. Good afternoon, everyone. I'm Jun Xiang from Team Singapore reviewing problem number 15, wet scroll. On to the report. Firstly, the reporter had investigated both the curling and the scroll formation and explained how both of these phenomena exist and provided a qualitative explanation for the significance of tracing paper in this phenomenon, explaining that it is because the tracing paper is dense, resulting in the dominant phenomenon being diffusion. The reporter then investigated the effect of surface tension on rolling and explained how it affects the meniscus, before attempting to explain deviations present in the predictions due to the stick-slip phenomenon. However, I believe there are numerous areas of improvement. Firstly, there appeared to be an inaccurate understanding of anisotropy. And I believe that because the paper can curl in both directions, the assumption that only one direction curls is not accurate, as it is simply the paper curls in one direction due to the expansion in one direction being much more significant. The reporter also had a poor predictive power of theory, as they fitted alpha, but they could have independently measured this by measuring the paper expansion. The reporter also had an inaccurate quantitative model that did not account for non-linear dependence of diffusion and had no account for curling in the machine direction, which, although small, does exist and affects the rolling phenomenon. There was no discussion on why the paper rapidly curls before slowly uncurling, and I believe that this is due to the initially steep water concentration gradient, resulting in initially fast curling. The reporter had poor experimental control, as the paper appeared to not be completely aligned with the camera, and the reporter also had no explanation for the further scrolling of the scroll, which I believe is a weakness. Onto the opponent clarified the unclear characterizations of constants used, such as the Young's modulus, and the reporter clarified that they characterized this. The opponent also attempted to clarify unclear definition of anisotropy before pointing out the reason for rapid curling and slow uncurling. Onto the areas of improvement, I believe that the opponent missed out the inaccurate quantitative model, as the report had assumed linear diffusion, which is inaccurate in this case, as the diffusion changes non-linearly depending on the saturation of the paper. And I believe the opponent brought up trivial points regarding the evaporation being significant, as the evaporation is insignificant due to the water being at room temperature and the fast time scale of the phenomenon, resulting in low evaporation. Lastly, there was a trivial point regarding the paper gaining moisture from humidity, causing some initial curvature, as the humidity will result in a uniform saturation of the paper. Onto the first discussion point of experimental control, I agree with the opponent that the string will affect the formation of the meniscus, and we can actually see this in the reporter's videos. I believe that this effect could be hidden in the theory experiment predictions due to the fitting of many parameters, and this indicates that this actually affects the phenomenon. Next, they discussed on the initial curvature of the paper, and I agree with the reporter that it is negligible, as humidity will result in the paper having a uniform water content, and this means that there will be minimal initial curvature. And however, I believe the reporter should have verified this experimentally, perhaps by taking a picture of the paper before placing it on the water. Next, they discussed on whether or not curvature returns to zero, and I agree with the reporter that evaporation is negligible due to the fast timescale of the experiment. Next, they discussed on the main driving mechanism for water movement, and I partially agree with the opponent that the capillary action could be significant, but I believe the reporter should have estimated the capillary number, which would have told us the significance of capillary action. Lastly, they discussed on the second curling of tracing paper, and I believe that this is due to the tracing paper slowly equilibrating to have a uniform water content after lifting out. And then as it enters the water again, the uniform water content will be disrupted by the water saturation at the bottom. In summary, the reporter gave a qualitative discussion of the phenomenon, but I believe that the reporter has failed to sufficiently answer the problem statement due to the attempted quantitative modeling, however, the poor predictive power. The opponent rightly pointed out the lack of explanation for the recurling, however, failed to provide his own explanation, and thus I believe he has not contributed significantly to the report. Thank you.
And about anisotropy, it happens because the paper expanded differently in different directions. That's why it is scrolling in that direction which it expands more. Then about obtaining the Young models. We did the experiment where we fixed the paper and we did it when it was wet. So then about qualitative explanation of rapidly curls and slow line curves. So it is scrolling rapidly because the paper is swelling fastly, but then it is distributing by the paper thickness slowly. About our estimation of linear diffusion coefficient. We estimated it because in our experiment, the diffusion coefficient was linear. Yes. So thank you for your time.
Okay, 1, 2, 3. Can we get your presentation back connected, the original one, and then can we restart the time for the jury questions? Okay, thank you very much. Please, jury questions. Anka, yeah, you, but not a new one, not for the previous report. Okay.
A question to the reporter. In the experiment where you investigated the curling speed, you had one of the side clamped with a clamp. Was this clamp in the water or above the water?
Above the water.
A question to the opponent: do you think the clamp above the water has a significant effect?
The clamp of.
If the clamp is above the water and does not touch the water.
I think it will, because she imposed the bounce.
Okay, thank you.
Okay, thank you, Patrick.
I have a question to the reviewer. You have mentioned that the effect of the water in the diffusion coefficient should be nonlinear. Do you have any physical insight why you would expect it to be nonlinear?
Well, this is because I believe that the water diffusion should actually depend on the pore size present in the paper, and thus there should actually be a scaling coefficient of the water concentration to the power of the pore size distribution index, and this would result in this sort of nonlinear water diffusion.
Okay, thank you, Vita.
To the reviewer, you seem to prefer capillary effect into describing this phenomenon. How would you suggest the reporter to include this capillary effect?
I'm sorry. This goes far beyond what was discussed within the presentation, because like they focused on the diffusion effect, and it's not the role of the reviewer to suggest how capillary should have been included. Carrie, and then Georgi.
Is this working? A question for the opposition. Would you consider that the ambient conditions, room temperature and the humidity in the room, to be very significant? And is it possible that when you did an investigation, might be very different to somebody else in another country? So it's done in a room?
Like yes, I think the temperature is very varied, and I think that in every region. So I think that temperature needs to take into account.
And the humidity.
Yes, humidity also.
Okay, Georgi.
Okay, that was basically also my question, but so I'll ask another question to the opponent. When you mentioned the initial bend because of the water vapor, do you think that it will give a significant effect?
Well, I think that the reporter also mentioned that the paper is not dry when initially. So I think that this should be taken into account. The curvature may not be zero, and like that affects the solution.
Okay, thank you. I have a question to the reporter. So if you can come to your references slide, then the paper which seemingly everyone in the room read contained a lot of information which seems to be similar to what you presented. So my question is, like, could you clearly state which part of your theoretical work is different from the reference number 1, and how did you manage to fit your data onto the theory, because the reference number 1 fails basically fitting the data on the first part of the event.
Okay, so in this reference, it is idea about the plotting kappa for short stripes, diffusion equation, and also the force parameters. And also in this in this paper, the diffusion coefficient is constant. But in our work, we have the expression for the diffusion coefficient. Then what we developed. The expression for the diffusion coefficient.
I'm sorry. I think like if you just need to read that one, then I think the jurors can read it and we can go further. Claire?
Okay, yeah, I have a question to the opponent. Once you said that random thermal motion plays a role here, do you think that your random thermal motion has some kind of a directional property, or is it going to be still in random direction?
I think that the diffusion equation is based on Brownian motion, and Brownian motion does not have a, it has a direction microscopically, but macroscopically it does not have a particular direction.
Okay, no more questions? Okay, then thank you very much. Let's have a big applause. Thank you. And please, again, the jurors start working now, so stay calm and give us a chance to give our grades. Miško, to je 3,5, tak môžeš dať štvorku. Dobre, a tuto si napočítal 7,5. Môžeš dať sedmičku.
A okrúhluješ dole?
Akože tu na hej, lebo podľa mňa toto sa malo jasne povedať. Ja potom pôjdem teda hore, dobre? Ak mi dáte, keď pôjdem na tribúnu to ohlasovať.
Dobre. A máš jak ťa ohlasovať? No ty budeš... Nie, to nie je tvoj.
Luka, uvedí yours.
Aha, tak si rovne natočím.
Okay, so again, we have the last juror having last 15 seconds to finish. Just don't fear under pressure. Yeah. Okay, it seems we are done. The grades for the report now: 5, 6, 6, 5, 4, 6, 7, 7, 7, 4. Grades for the opponent now: 6, 6, 4, 6, 7, 8, 8, 6, 6, 6. And grades for the reviewer now: 9, 9, 6, 6, 8, 8, 7, 9, 9, 7. Okay, Georgi, you deserve a mic.
Oh.
Yeah, it's running.
One. Okay. So my main issue and why I didn't go higher than 4 was discussion. And so like I gave very few points in discussion, and like the presentation itself like wasn't very good in the finals, like even for the presentation with Poland, and for this presentation I expect like something even better and some extra works to be done, but like it was decent and it was okay. So I gave like 3 in the report part, 0.75 in the discussion, and minus 25 in the questions, and like it was a 4.
Okay, I also gave a 4. Yeah, it's like a rather low grade for, especially for the finals. But first of all, I had to, justify my grade also comparing to the previous presentation, and I think like still the previous one was better than this one. And except of what Georgi said, I can subscribe with that. You really didn't prove in some sense that you understand and you are say really at home in this problematics. I do have several concerns concerning the results itself, like knowing that paper and many other papers around and many other data around. I do have several concerns whether your changes which you propose to the theory could lead in such a good fit between the theoretical prediction and the experimental data. Let's leave it on that position, but I couldn't score you more than 4. Anyway, we had a 7. So Jan, for instance.
Yeah, so I gave a score of 7. I think in terms of the report, I thought it was like overall good, especially compared to the ones that I've seen during the selective matches. I felt like what could be improved in the report is on the qualitative explanation and so also on the science communication. I felt like there were a lot of equations that was presented. You could have spent some more time explaining it. And I thought, you know, I think even until the end, we weren't very clear on, you know, what's the phenomenon, like what's the mechanism that causes this repeated curling and uncurling. So that's why I couldn't give you like a higher grade. I feel like the discussion with the opponent was slightly lacking. In my opinion, you could have like presented some more evidence to address the concerns that the opponent raised. So my partial grades were the initial 5 for the report, 1.5 for the discussion, and minus 0.5 for the questions.
Okay, thank you very much. Then time is running quickly. Let's proceed to the opponent, the usual suspect, Patrick.
Hi, so I gave you 0.5 for the questions. I don't think that the questions that you have asked was very relevant because you were mainly asking, did you measure that parameter? Did you measure that parameter? Did you measure that parameter? And I think you could have asked more relevant questions. Then your speech was an average of, in my opinion, so I gave a 2 for that. It was a bit chaotic, so we were jumping between topics very fastly. Yes, and I really didn't like your discussion with the reporter because during the discussion, it was mostly that you only asked questions. It was no real discussion, only you asking questions, then she trying to answer, and then you asking the next question. And in my opinion, you focus too much on unimportant topics, like you spent 1.5 or 2 minutes about the definition of what a diffusion is, also on what evaporation is or how important evaporation is. And if you bring up a new topic like evaporation, you need to convince me that it's important because it is the reporter who has done the experiment. She mentions that it's not important. And if you bring the topic up, you need to convince us that this is actually an important effect.
Okay, thank you very much. Sergey, you seem completely agreeing with Patrick in your like face, but not in your grade, so.
Yes, for me, I do agree with many of the points. Maybe with the relevance of these points, and there's where the grades deviated. I thought when discussing the results, yeah, I agree completely that the opponent, if he brings up new topics, should make them relevant, and also should ask the reporter in what way to explain why they are not relevant. And in this sense, I gave more points for the discussion because when the reporter said, okay, but we did measure this and showed the graphs, and the graphs had good fitting, the opponent didn't press this any longer. He did bring new topics without convincing us that they are important, but then accepted the response that they weren't so important.
Okay,
so, yeah.
So very briefly from my point of view, lacking your opinions. You summarized nice, etc., but like there were lack of like your position towards that. Anyway, the review was generally marked a bit higher than the rest. So for the 6, can Kerry comment, please?
Yeah, sure. So for the review, I thought the questions, I gave it a 1. They were okay. But the presentations were quite nice. But my big concern for this problem was that we have people from different countries working with possibly different pieces of paper, which have very different histories. And this was a really vital thing which should have been pulled up by the opponents. Different ambient conditions, so many different things, and you didn't go in and point out that this was missing from the debate, and I would really like to have seen that. So that just pulled you down a bit.
Okay, thanks. It's just one person per lowest and one person for the highest grade. Otherwise, we never finish. Eric, the 9.
Yeah, so considering the limited time the reviewer has, I thought that you did a really good job in pinpointing the most important aspects of this phenomenon, or it was the most productive phase in the whole fight, I thought. So your questions were really good, in particular, for example, on the clamp positioning, and also the analysis of the report and discussion was fine. The only part I was a bit concerned, but everybody struggles with that, is the review of the opposition. So somehow that's a common theme. So I give you 2, 2.5, 125, 175, 0, 0, which is 8.5, and I always round mathematically.
Okay, thank you very much. That's it for this round. Thank you very much. Let's have a big applause now again. And let's have now 10 minutes in SI units, so real 10 minutes. and Poland reviewing. Okay, so if everyone's ready, then let us start 5 minutes of preparation time for the reporter. If you are ready earlier, just let us know when we can start.
Wait.
Hi. Okay, I think I'm ready. Hello everyone, I'm a reporter from Team Taiwan. I'm here to report the problem number 5, ping pong rocket. Problem statement, a ping pong ball is placed inside a container of water. When the container is dropped, the ping pong ball gets launched into a great height. And what's the maximum height you could reach with up to 2 liters of water? So for our parameters, I'll be focusing on to optimize for a maximum height will be the container shape, initial height, water volume, and container radius. And the key question of this problem is, why is there a jet focused in the middle? And I'll be calculating such a jet and optimizing to find the max height I could reach. So for my experimental setup, I just lean my container onto a wall so that the wall corners will guide the container so that it will have a best contact angle with the ground. And sometimes adding dye into water to better show the water motion. But the real experiments are done with pure water, with tap water. And I adding an iron ring to make sure the ball stays in the middle so that the jet could hit the ball in the middle. And I did experiment to prove that the friction of the wall would be negligible and the standard deviation will be less than 10%. And also, I made sure that the jet will have no effect on the jet formation, making it the ring helping the ball stay in the middle and not affect the jet. So here's observation. When I drop it 130 centimeters, it will get launched into 169 centimeters. So the height got increased by more than 500%. And also, there will be a focused water jet in the middle, which pushes the ball up. So first, I'm going to talk about my quantitative launch process about why is there a jet forming. So I have these different phases. So during rest phase, there will be a slight contact angle due to the cohesive force and adhesive force balancing out. And that will be very important in our later jet formation. And also, during this phase, the ball will drift on the water. So that will be the importance of adding an iron ring to make sure the ball stays in the middle. And during this phase, the gravity will dominate the entire field, making it dominating by gravity. But during a free fall, because of the absence of gravity during the fall, everything is weightless, and so the other forces will be more dominant because the gravity is gone. So the first force we come about is the adhesion force, which is the pull from the wall. So the water will get pulled to the side, making the water surface kind of climb on the wall. So you can see from a simulation I have and the photo I took, the water is climbing on the wall. And also, because originally there will be some hydrostatic pressure, which is a buoyancy, which is caused by the gravity, it will disappear in a free fall. So the ball will actually get pulled into the water due to a surface tension. As you can see in the photo I took, the ball is sinking. And when it hit the ground, you might imagine the even force from the ground would give it like an even water jet like this. But in reality, the sides will be affected by a boundary, which kind of has a pull on the water, which makes the sides remain on the wall due to adhesive force, which is the pull from the wall. And the middle is the free surface, which goes up, forming a jet. And the jet is the main reason of the launch because it pushes the ball up and will display the focus pressure. And also the water gets pulled into a jet, as you can see in the simulation right here. So now I want to do a quick test on confirming the adhesive force actually affects the jet formation. So as you can see, I have these three different materials of tubes, and one is hydrophilic, glass, and hydrophobic. And adhesive force, the philic being the strongest, then glass, then phobic. And we can see hydrophilic barely form a jet because the pull from the wall is too strong. The middle surface is not free. While glass form a very perfect jet as we wanted, while the hydrophobic, because the pull from the wall is so weak that there will be no jet. So now we could confirm that adhesive force between the wall is very significant for our jet formation. So here's our model summary. So the ball is here to represent the force focused in the middle, and the water is going to add gravitational energy and transfer the energy by jet, and the container is here to limit the water movement and focus the jet. And since the ball is pushed by jet, I'll be focusing on calculating the jet formation. So now I'm going to talk about quantitative jet formation. So my approach is to fit a function into a jet shape, and because that could calculate us for the velocity field of the water. So I'm going to compare these symmetrical and focused and middle functions, which includes Gaussian, Lorentz, and Basel. And fitting with the picture I have, we found out the Gaussian is the best fitting, and also it very well describes the turbulent flow. So I'm going to use Gaussian to my later theoretical calculations. So my main idea is to transfer the mass flow rate going up, to calculate it and retransfer it into a jet formation as a velocity field. So according to conservation of mass, the velocity profile of the jet flow could be written as this, while the max here is the middle of the jet, which is the maximum velocity of the entire field. So by knowing the velocity of the jet, we can now calculate the flow rate of jet on the ball. And the main thing I want here is the average velocity of the jet, which could be calculated as this U bar. And I want to transfer this to get that. And so it could be calculated with this equation right here. And the radius of jet, with the blue radius of jet, will be calculated by dimensional analysis and calculating the effective area of jet. And using integral on the Gaussian function, we could get the radius of jet to be that equation. And thus, we could also calculate the maximum height of the jet. But in this case, it will be irrelevant for us because we want to know the velocity of the jet. So knowing the velocity of jet, now we can calculate momentum conservation of how much the jet's actually transferring its momentum to the ball. So for the mass water mass ball equals to these equations right here. While the delta z squared, the delta z means the contact with the ground sink amount minus the rest phase sink amount, which will be a gain sink amount during a free fall caused by the surface tension I just talked about. So we'll be calculating with this equation, and it's a linear relation with the initial height, and we're just gonna use found by experiment. And so knowing the momentum of the ball, we could calculate the velocity of the ball to be this equation, while alpha here is the potential energy. It's considering the weight of the system, and it's done by from experimental, and I confirm it to be using this. And for the sigma here, it's the spread length of the jet, which has a direct relation to the focusedness of the water jet, and it's affected by container radius, and I'm just going to fit a line with my measurements to draw my theory line better. And so here's the sink amount, and here's how it transfers from jet to a ball. We could also, so knowing the velocity of the ball, we could calculate max height to be this equation right here, considering the air resistance going up. So now, knowing all the theories, we can now do our experiments to optimize my maximum height. So I want my maximum height, and the parameters I'll be optimizing is the shape, initial height, volume, and diameter of my container, and I want to find what is the positive effect. And I'm going to optimize my experiments by tracking the exit velocity because it's easier for me to do. And faster velocity means higher height, and I'll be showing everybody the maximum height in my conclusion. So the first experiment, I 3D print my containers to different shapes, including circle, triangle, square, and hexagon, and make sure they have the same top area and the same weight. So here are the results. We can see that the circle best matches the theory, and it matches my simulation also. And the explanation for this is I talked about how the wall will have a pull on the water, and as you can see, the triangle will have a very strong interference on the jet formation because the jet is, you can imagine it as focused in a single point and has a gradient decrease to the outside. So if it's a triangle shape, it will have a strong interference to the jet, while you can see for a circle, it will interfere the jet to the least. So I'm going to use the circle. Then I'll be changing the initial height of the container. So we'll see from the results. My theory says if you go higher, you should have more potential energy, which makes the velocity go higher. But my theory reached a peak. It's because, as you can see, as I talk about the adhesive force during the falling, the water will climb on the wall. As you can see in the video right here, it kind of climbs on the wall. And if it's dropped from if it's dropped from a very high height, too much water is climbed on the wall, which left no water left to form a jet. So there will actually always be a peak for initial height. Next will be our volumes of water. So I'm going to use the same container, but adding different volumes of water. So here are my results. So the theory says if you have more volume, you should have more potential, that which transfer to higher velocity. And my results will agree with the relation. But by reviewing our last two experiments, by changing the initial height and water volume, the thing that actually changes is the potential energy. But the potential energy, both of my theory overestimates. So my hypothesis now is maybe the potential energy will affect the spread of the jet, which will better explain why it look like this. So if I could fit sigma, we could get a very good theory line right now. But I want to explain why. Now I have a very accurate theory. What does fitting sigma mean is actual physical meaning. So my original assumption, when potential energy increases, I thought the jet will only increase in the middle direction, which makes the jet faster and stronger, which pushes the ball higher. But my new conclusion by fitting sigma, now we know by increasing the potential energy, actually a lot of energy will get wasted to the side, which has no direct help to actually push the ball higher. So by knowing all these, we can know that more volume and more height means more potential energy, while more spread means more energy loss. So I can have a guess of this, the shape being less diameter shape will be better than that one due to it being more focused if they have the same potential energy. So that leads up to our final experiments of changing the radius of a container but using the same amount of water, which I control the weight of the container. So we can see from results. So the theory says if your container is smaller, you should be more focused. But my results does not match this in a very small diameter range, and I'm going to explain why. So first, we need to go back to why is there a jet? The jet is formed by the velocity difference from the side and the middle. And according to my theory, if the same force hit a container, the small diameter container is going to be more focused. But there's a limit to this small diameter container. If it's too small, the two sides will be too close to each other. You can imagine a gradient velocity will look like the picture I drew below, that it cannot reach its maximum velocity in the middle due to it being very close to the all-around wall. So you can imagine as the bigger diameter container has a more of a free surface, while the smaller diameter will be affected by the wall and not form, it will kind of get pulled by the wall and not form a good jet. So now we can know the small diameter means less spread, which is good, but there's a limit to this. The diameter cannot be smaller than 9 centimeters. So let's go to our conclusion. So the problem statement wants me to investigate what is the maximum height I could reach with up to 2 liters of water. So I explained the launching mechanism of the rest phase, and it's due to the there will be a contact angle, and the cohesive will balance the adhesive. And for buoyancy, there will be a hydrostatic pressure due to gravity. But during fall, the buoyancy disappears, and other forces will be more dominant, such as the water will get pulled to the sides, which makes the water climb on the wall. And sometimes it will have a bad effect on the results. And also, the ball sinks due to the surface tension because there's no more hydrostatic pressure. And finally, when contact, the adhesive force will make the sides remain on the wall and make the middle launch up, which pushes the ball up. And for my modeling, I model my jet by Gaussian function. So because it's a turbulent flow, I could use my I have fitted with the results. I found the Gaussian would be best. So I transfer the masteroid into a jet formation and get the equations right there. And for optimizing my parameters, so I found out the circle being the less interference for the jet formation, while the maximum height is finding the balance between the potential energy and the adhesive force, which makes the water climb too much on the wall. And for a 2-liter water, it's the most potential energy. For radius for 4.5 centimeters will be the best balance between the focus of the jet and adhesive force, which is cannot be too small of a diameter. So by combining all the things we know, we could get the best. Here's the best parameters I could find, and the maximum height I could reach is 7.65 meters. And actually, if you're wondering, I could solve with these parameters and solve to be 31 meters per second and get a very close theory with my experimental data. And that's the end of my report. Thank you.
Testing. Okay, thank you, reporter, for your report. Firstly, can I ask, what is the maximum tilt of your container at impact?
I control it to be 0.
Okay. Did you assume a purely elastic impact of your container?
I assume my container to be a rigid body.
Did you assume an elastic collision?
Oh, yes.
Could you go to the last slide where you predicted your maximum height? Am I right to say that parallax would be significant?
The what?
Parallax. Is it significant?
What, can you tell me?
Okay, parallax error due to the perspective. Okay, never mind. On to my next question. Does sigma change over time?
The sigma here is the fully developed jet.
How do you define a fully developed jet?
So you can imagine as the biggest sigma of the entire jet flow.
So how do you define when the okay?
Yeah, so I record a video and the biggest sigma is the fully developed jet.
How do you define when in time is a fully developed jet formed?
When the sigma is bigger, so the sigma is biggest.
So you track sigma over time?
Yes, I record the landing.
I see, okay, thank you. What is the impact velocity of your container?
It will be affected by potential energy.
So you assume conservation of energy using your drop height?
Yes.
Okay. Did you consider buoyancy force acting on the ball?
Yes, I did.
During launching?
Yes, I did.
Where can I see an equation for buoyancy force on the ball at impact?
Yes, so...
That is not buoyancy force, that's only considering conservation of momentum.
Oh, okay, yeah.
Okay, thank you. Can you go back to your simulation on the different cross-sectional shapes for your container? What do you use to simulate your different containers?
You mean the software?
Yes.
It's Flow 3D.
I see. Okay, thank you. Did you? Okay.
所以你碰撞能量是怎么算？你是算 impact velocity， 然后就直接一定是非常高。那你能量，那你撞到地上之后能量损失去哪？
Please, can I ask you again to calm down during the preparation phases? They need to work. Thank you very much.
take the biggest sigma.
Does the volume also the turning point? Yes, the volume. No, move that under optimization. Optimal sheet of container, yeah. Yeah, they did. No, I dump that point. No, I just leave it. Volume and sheet. Just pick the most important. Oh, time dependency. Can we put that under graph? Can we put that as a new point? Yes, what do you call it? Time dependency. Yeah, sure. Like, what affects it? Can. Actually, wait. Should I write the summary? Wait, should I write the summary so that I can rebut the stuff? Is the font big enough? Yeah, can you make the font big enough?
Good morning, everyone. I'm Christopher from Team Singapore, and today I'll be opposing problem number 5, ping pong rocket. Onto the report. The reporter managed to qualitatively explain the significance of dropping the container in that the meniscus, there will be a meniscus formed in the, as well as the sinkage of the ball during freefall. He also managed to explain the reason behind why a jet forms in the container when the container impacts the ground. He also quantitatively modeled the jet by fitting Gaussian to the jet profile in the container, as well as use conservation of momentum to find the energy of the ball and hence the maximum height. He also experimentally varied the different parameters and investigated and tried to optimize them. On to the strengths of the report. Firstly, I commend the reporter for attempting to quantitatively model the jet. I believe that this is actually quite difficult, as you would have to as the jet is a very significant part of this phenomenon, as the reporter has mentioned. As such, accounting for the profile of the jet and hence the energy and velocity of the jet would be very significant in its contribution to the ball's final velocity and hence maximum height. He also managed to explain the different phases of motion and why they are significant to the phenomenon. For example, the free fall phase leading to the formation of the jet. He also managed to experimentally measure the contact angle of the water with the ball, and I commend this, and I commend the reporter because I believe that this significantly affects the surface tension force on this ball during free fall, which would affect the sinkage depth and hence the buoyancy force. However, he also did not mention on the buoyancy force, which I'll talk about later. He also had a wide experimental range, which is very important for the main point of this problem, which is to optimize the parameters to get the maximum height. He managed to vary the different shapes of the container, as well as the different volume of the water, drop height and radius of the container, which I commend him for. Now onto the numerous areas for improvement of the report. Firstly, the reporter had a poor experimental control, as we can see from all of his videos that the container tilts before impact and as well as after impact. And I believe that this is very significant because this can affect the formation of the jet within the container. If the container is slightly tilted, the jet will not form in the center of the container, hence the energy transfer from the water to the ball may not be as efficient as the reporter predicts. On the point of parallax, this is also very significant in how he measures the final maximum height of his containers. For example, if we go to the last slide, we can see that parallax error is very significant. Secondly, he also had an unjustified fitting constant in the form of sigma for his jet profile, and I believe that this weakens the predictive power of his quantitative model, as he also later says that he takes sigma as a free parameter to further fit his theoretical prediction to his experimental data. We can also see from his videos that the jet profile is not exactly a Gaussian profile, and hence fitting a Gaussian profile is also not very significant. He also neglects the ball detaching from the jet, which results in less energy being transferred from the water to the ball, which will affect the maximum height. Third, the reporter also assumed elastic collision between the container and the ground. And I believe that this is very important because we can see from his videos that firstly, the container does not rebound to the same height, which means that it cannot be an elastic collision. It has to be inelastic. Secondly, we can also see from his slow motion videos that the container is deforming at impact, which would have resulted in more energy being dissipated, and hence less momentum being transferred to the ball. Lastly, there was also no consideration for the buoyancy force acting on the ball, although the reporter says that it is very significant when considering the movement of the ball during the free fall. Lastly, there's also a slightly inaccurate explanation for the optimal container shape, which I'll cover later. Now, I'd like to invite the reporter up for discussion. Firstly, I would like to discuss the poor experimental control in your setup. Could you go to slide 12? We can see that your container is, could you play that video? It's okay, I'll leave this. Could you play the video? Okay, we can see from your video that the container is slightly tilted as it impacts the ground, as it's not perfectly flat. And we can see this even more because the container rebounds and tilts even more. So I believe that this would have caused the jet to be not formed in the center of the container. You agree?
But that's after the collision. But as you
we
can
see that the container is tilting before the impact.
No, that the jet.
Could you explain why the jet is not formed in the center of the container?
It is because the container is tilting after it collided.
Then could you go to slide 3? Okay, we can see slightly better that the container is tilted at impact, which results in a further tilting in this direction after the impact, correct?
Yes.
Okay, so that means that the jet will not be formed in the center of the container. Because if you imagine a container at impact, imagine this is the ground, the jet will no longer be able to form in the perfect center of the container. Instead, it will be forming somewhere slightly to the side, correct?
Yes, if it's not in a perfect contact angle.
Correct, right? And this is because the water cannot converge at the center of the container. As such, I believe that if your ball is centered in the middle of your container, as you have with your iron ring, that the jet will not form directly beneath the ball, correct? And this may result in the jet not being able to efficiently transfer energy from the water to the ball, resulting in several over-predictions in your theory.
That's correct.
Okay, good. I'm glad that we clarified this point on the poor experimental control. I believe that you could have reduced this tilting of the container by possibly using guide rails to ensure that the container lands vertically on the floor.
Yes, but through my experiments, it's pretty reproducible.
Okay, I'll now like to move on to my next point. On the lack of qualitative explanation for why the jet forms, you mentioned in your report that the jet forms because all of the water is being moved up at the same time. However, adhesion results in the water at the sides not being able to move, correct?
That's correct.
So, however, I believe that this is slightly inaccurate because you also mentioned in your report that the water sort of forms a curved shape due to surface tension, right?
Yes.
So, what do you think happens when gravity starts to act on this water surface at impact?
So on the impact, I just imagine the sides staying on the wall while the middle just go up because it's like not pulled by the wall. So that's just
But gravity would also act on the water here, correct?
Yes.
Like gravity will act here and here, correct?
So you're saying that the water on the sides will also get into...
Yes, that's correct. So what I'm saying is the water will be pushed down, and then because of incompressibility, water will flow towards the center.
Yes, I have a simulation just to show that in my
but did you quantitatively model it in your theoretical model?
No, I did not.
I see, okay. But I'm glad, firstly, I'm glad that we agreed that this is a better explanation as to why the jet forms. And you also did not manage to account for this mechanism in your quantitative theory. I believe that you could have modeled this phenomenon using by modeling the water surface using sort of like the Young's Laplace equation, not accounting for hydrostatic pressure, which would have given you this shape. And then you can apply a gravity to simulate the water converging at the center.
Yes.
Yeah, okay. On to my next point on ball-jet interaction. Onto my next point on ball-jet interaction. Would you, in your simulation, you, in your experiment, you also showed that that the different types of, the different like sort of maximum height the jet would form in, based on your contact angle, correct? Could you go to that slide?
Contact angle?
You talked about hydrophilic, hydrophobic, and contact angle being
you mean
0.
I changed the container's material? Like the, okay.
Yeah.
Wait.
That slide. Yes, this slide. Okay. However, you mentioned here that it is due to these forces that results in the jet being significant, correct?
Yes.
But did you ever investigate into how the jet is coupled to the ball? Because if let's say you were to how do I talk? Your ball would prevent the water from shooting up, correct?
Can you further explain
like, okay, so you can imagine the jet on its own. So this is what your experiment is showing, correct?
Correct.
Okay, then what do you think would happen if, let's say, we add a ball on top of the water?
Oh, you mean, so are you saying the ball's weight, or what are you talking about?
The presence of the ball. Okay, yes, the weight of the ball.
Yeah, so that's why I calculated the momentum conservation. And yeah, I consider a ball's weight in my theory.
No, as in, do you think that the presence of the ball would affect the shape of the jet?
Oh, yeah, I agree.
Could you elaborate more on what you mean?
Yeah, it's definitely, yeah, as you're just saying, like if there's a jet and you put a ball on it, definitely the jet shape will be different.
Okay, so we both agree that, let's say, if we put a ball at the top, that the water pushing up on the ball would be sort of diverted to the sides, correct?
Yeah.
Okay, so then this will result in a not so Gaussian profile jet.
Yes, so the Gaussian is there just to approximate the velocity field of the jet, and for after, I don't think I don't think that will be much of an effect because the Gaussian just calculate the velocity.
I see. Okay.
Yeah.
Okay. Let's agree to disagree on how the Gaussian shape of the jet would affect the momentum imparted to the ball. I'd like to now move on to my next point on the buoyancy force. I realized that in your quantitative model, you did not model the buoyancy force on the ball. Do you think that it's significant compared to the momentum transferred from the water to the ball?
I think it will affect because in my theory, I also calculated a sink amount, which will have an effect on the buoyancy.
So you calculated the sinking amount of the ball, but you didn't use this sinking depth in the rest of your quantitative model to include a buoyancy force on the ball.
I think
right, because I believe you use conservation of momentum. Yeah, so am I right to say you did not include buoyancy force?
Yes.
Okay. Okay, then I believe that this is actually quite significant because buoyancy force, in this case, I believe is the dominant force. For example, we know that the buoyancy force is calculated as rho Vg as a simplified model. In this case, we have 10 to the 3. Your volume, could you give a rough estimate of the volume displaced?
The ball's radius is like 2 centimeters. Like
sure. Okay. So then we can do something like 2 pi 2 centimeters squared cube. Sorry. Then I believe that this we also cannot use the regular gravity 9.81 because at impact with the ground, your normal contact force on the container will also contribute to a much larger sort of effective gravity, right? Would you agree? Like in the frame of the container, there will be if you look at the container, there is a normal contact force on the container,
yes,
right?
Yes.
So then, in the frame of the container, what would the ball and the water would see is sort of an additional force trying to pull it down. So in this case, it would be sort of like effective gravity.
Yes, and what would affect that effective gravity?
I believe that because the container is rapidly changing in velocity, so your effective gravity will be much more significant than simply 10. So it probably, I can give a rough estimate of around 100. So we can clearly see here that it's already around more than 10 to the 5, which I believe is a very significant buoyancy force that you did not manage to include in your quantitative model. So I suggest that you could have modeled something like this to include it in your quantitative model. Lastly, I also like to talk about your time-dependent jet shape. Sorry, well, my last point on optimization, could you go to your slide on optimizing the shape of the container? I see here that your qualitative explanation is slightly inaccurate. I believe that it's because water is converging at the center of the container at different times, which is why you don't have a peak force.
Yeah, it's the same. So I said this will be having more interference on like a perfect jet shape.
I don't mean different in. Okay. In summary, the opponent and I, the reporter and I discussed about his lack of experimental control in that there was tilting of the container as well as parallax error, and I believe that the reporter could have made simple additions to his experimental model to improve his experimental setup to get more accurate data. We also discussed on the interaction between the ball and the jet. And I believe that because the jet is pushing the ball, this results in a deformation, and it's not exactly a Gaussian profile. I also believe that the jet could also be pulling on the ball due to surface tension between the ball and the water. And as such, a more comprehensive quantitative model would be required. We also talked about the buoyancy force being very significant due to the large change in impact velocity and rebound velocity, and I believe that he should have accounted for this in his quantitative model. Lastly, we also talked about the optimization of the parameters, and I believe that it is very important to get this qualitative explanation correct because it does affect the optimization of the container shape, which is significant in this report.
Question for the reporter. Did you investigate very large containers? Why?
The biggest I have is 9 centimeters for radius.
So can the phenomena occur for the moment when you have the hydrophobic surface but the ball inside?
Now the jet will be very unfocused. As you can see, you can imagine a very unfocused kind of jet. So.
But there is a jet.
You could classify it as a jet if you could classify it as a jet, I think.
So question for the opponent, is the surface tension that important when you have a ball inside?
What do you mean if I have the ball inside? Like, is surface tension significant during the launch?
Can the ball inside of the container affect the existence of the jet?
I believe that it is not so much surface tension, but rather because the jet is trying to push upwards and the ball is trying to is an opposing force on the jet. Hence, the jet would sort of diverge below the ball, resulting in less momentum transfer to the ball. So if the surface
is flat, but there is a ball, you believe that there can be a jet?
Yes, I believe that can be a jet because of the high gravity resulting in water from the sides being able to converge below the ball.
Question for the reporter. Does the Gauss that you fitted have some physical insight, or is it just a fit?
I think if you're talking about physical insight, I think the turbulent jet is very similar in Gaussian function for its central limit theorem.
Question for the reporter. What was the time of the collision? Did you measure that?
No, I did not.
Okay, question for the opponent. You said that the elasticity is important. What would happen if you had the rigid container?
What will happen if you have a rigid container? I don't think it's more on the rigidity of the container affecting it, but rather because the impact of the ground is inelastic, so there will be energy loss at this impact, which means that he cannot use conservation of momentum from the initial drop height.
All right, so a question for the reporter.
So if it's a rigid container, I think it might go higher.
All right, so there will be no another phenomena that will occur. Okay, so can your theory predict maybe what happens if you drop the box not really precisely? Could your theory predict what happens if the jet would be on some other side?
I think it will still be like in the center of the container, but if you drop it in the side, the center will be moved to the sides.
So if you place the ball not in the center of the container, the jet would be still in the center of the container?
If the dropping is not in a good angle, it's definitely not the
I mean, if the ball is not in the center of the container, is the jet still in the center?
I think the jets need to fully hit the ball in the middle for max height.
Same question for the opponent.
I believe that if the ball is not in the center of the container, the jet would not form in the center of the container. It would form somewhere else. It might also not be below the ball.
Ladies and gentlemen, my name is Zofia Lemelska. I represent Team Poland. It's my great pleasure to review the problem number 4, ping pong racket. So first, I would like to start with the pros of the reporter. And what we have seen was a first great theoretical explanation and made a theoretical model about the jet and how that impact affects the jet formation and how the momentum is how that force of the jet affects the ball, and therefore the height of the impact. And then we saw some experimental setup, and they were able to drop the container from the height, and they were able to control that very well. What we also seen was the investigation, how the contact angle affects the jet and how that jet would be formed. We saw that the jet won't be formed for the moment when we have the hydrophobic surface, but we will see it is the hydrophilic. However, what I have missed there was maybe the explanation why the jet is even formed. We saw that it is formed, but we didn't have an investigation how maybe the fact that the ball is inside affected, and it is crucial that we have the difference in the pressures, and therefore there's a jet formation due to that fact that there is a difference in the hydrostatic pressure, and therefore the difference in the value of that momentum change. And I would like to really see more of the investigation what physics really works for the jet formation. What also we have really seen that did very well, that they didn't allow the ball to fall. There wasn't the good collision, the container didn't fall fully perpendicularly, and therefore they couldn't have a good experiments. About the opposition, the opponent pointed out that theoretical model ignored the hydrostatic forces and only investigated the momentum change. And also they pointed out that it is very important that we should investigate maybe where the collision is elastic and whether the collision is rigid, and we think that it is crucial about the energy change. However, they didn't really investigate maybe another phenomena as such as the cavitation that could also occur, and we wish they could pursue that topic a little further, so they would really get into the physics that occurs there. They also didn't really bring up the fact that we don't really know how the jet is even formed, and we would really like to see maybe some explanations of the things that the reporter didn't say that during the presentation that are crucial for the problem to even occur. And also they pointed out that the buoyancy force is much less important than the impact flow, but we don't really agree with that. The time scale of the phenomena is so short that the buoyancy force won't be that important. And in the discussion, we had three major topics. First, it was the position and the shape of the jet and its inaccuracy. And we think that it is very good that the opposition pointed that out, since it is the crucial that we have the centered ball. So we have the actual measurement of that height for the accurate measurement. And maybe we could also see some investigation how the different position would affect that, since it affects the jet formation. Then it was the topic of the actual formation of the jet. And we believe that it is that flow from high water levels to the center that creates the flow. And it's crucial that the jet may occur even for the flat surface when the ball is inside, since it also creates the difference in the pressure and creates the jet. And the third topic was the effect of the ball on the jet. And we believe that the ball not only affects the motion of the jet, but also the formation of the jet itself, which is very important to be investigated, also that important factor, and it could affect the theoretical model of the reporter. And what was really missed in the presentation was the ball's effect on the surface shape and the jet formation, and investigation of that topic, which is crucial for the actual understanding of the problem. Thank you.
So first, let's talk about what I did in my presentation and my own contribution. First, I explained the different qualitative phase of the launching motion. So during the rest phase, the gravity will dominate, and during the falling phase, because absence of gravity, other forces will be more dominant, including water going to the side of the wall and the ball sinking. And for a cohesion, collision. So the adhesive force will remain on the wall and making the middle side only go up because the adhesion force of the middle water is very small. And for my later 3D model, I used Gaussian function to fit the jet as my velocity field, and my best container shape would be a circle. And the overestimation of the height and volume is due to not assuming the sigma is constant, but after fitting the sigma to be another linear relation, it fits my theory very well. And for combining all my parameters, I find my max height to be 7 meters. And for the short question, so my sigma is taken for a fully diluted jet, which I define as the biggest sigma throughout the whole jet. And I assume the container as a rigid body. And I didn't use the elastic collision, only conservation of momentum. But during such a short time, I think it's still possible to use, and use Flow 3D to simulate. And for later discussion, we talk about the tilt of the container may cause a little deviation, but in my experiment, I tried my best to control the hitting angle, which I think I did very well. And for gravity acting on two sides, because the water is pressable, so the water on the sides would also flow into the middle, which I proved in my simulation. And the Gaussian is here only to calculate the velocity field of the jet, so the ball presence will not affect the Gaussian distribution. And the buoyancy is considered by calculating the sink amount calculation. And we know the circle shape has a less amount of interference for jet formation, which makes it launch higher than the triangle, square, and hexagon. And finally, we'll talk about the hydrophobic containers in its effect. And the hydrophobic container make the water don't remain on the wall, making the jet very unfocused or not significant. And that's the end of my remark. Thank you.
One, two, three. Thank you. Please, can I have the reporter, opponent, and reviewer on the stage, and the presentation connected before we start the time? Thank you. Okay. Thank you very much. And please, Patrick, and then Eric. No, sorry, then Anka.
Can you please go to the slide where you do your highest launch and then the comparison with the theoretical value? It's one of the end of the conclusion
Yeah,
slide.
30 something.
So my question is that you are not including the effect of the surface and also the rigidity of the container. So how much is the overfitting here? So how can you get this good theoretical prediction when you are neglecting these types of effects?
So the main thing here, I think the only is a sigma, and which is it's a sigma.
Okay, just a very quick question. Is like if you repeat your experiment 10 times, so what's the fluctuation of the results? Like if you because you said the haze is 7.65 plus minus what?
Oh, I found my standard deviation to be around 10%. So, but this, yeah.
Okay.
Yeah, my question was, since you claimed that your experiment was reproducible, each measurement point where you had an error bar, how many individual measurements went into this?
I did 10 times.
Okay, thank you.
Okay. Could you show me the slide where you have this momentum conservation within the jet? So I presume that's one. No. Okay. Okay. This one. So do I understand it correctly that you have like the mass of the ball plus the jet? And then all the momentum goes to the ball and the ball is accelerated?
Yeah, that's how.
Okay, but isn't it true that in such a case the energy of the ball, because it goes with square of the velocity, is higher than the common energy of the jet and the ball before?
I'm sorry.
If you have two balls moving 1 meter per second, and then you transfer the momentum into the one ball moving 2 meters per second, you gained energy. And my question is, where does energy come from? You conserved the momentum, but you went into a way when the energy was increased. And my question is, where did you get the energy?
Can I answer?
Yeah, sure.
I think.
Yeah, just you answer. It was just like the next question. Please.
I think that the energy actually comes from when the bottle was dropping and the potential energy goes into water and water goes into the ball. I think that is where the energy comes from.
Okay. Patrick?
I have a question to the reporter. For the reviewers' questions about is there a physical insight behind this Gaussian jet? You have mentioned the central limit theorem. Can you please clarify a bit more on this?
So I think the main thing is like the jet is a turbulent flow, and the turbulent flow, which will represent to chaotic and unpredictable flow, but it will end up like a Gauss. So that's the thing I was just trying to say, of it being a turbulent flow.
Okay, then whoever has the working microphone.
Okay. Okay. So is your water in this model compressible, and did you account for compressibility or non-compressibility of the water?
This water is not compressible.
So the volume in all your models remains constant, the volume of the water.
Yes.
You did account for this?
Yes.
Can you show me where?
I didn't account for this, but the volume would be the same.
Okay,
Sure
Georgi?
Okay. On some slides you showed the velocity profile from the simulations. And like I'm asking, like, did you do the simulations and or was it like found somewhere or on some engine, or like if you did, like what were the equations that you based those simulations on?
Oh,
it's that one.
Yeah, the simulations use Flow3D, and Flow3D is calculated by using Navier-Stokes equations.
Okay, thank you.
Vita?
Okay, what is the force that pulls the ball down during free fall?
Surface tension.
Okay. No, okay, Patrick still has one. Okay, you have a chance.
The reviewer has mentioned that the timescale that the buoyancy force is acting is much larger, so it's negligible. What would the opponent say to that?
I believe that this is not negligible. Just now I calculated that the force would be 10 to the 5. And I can estimate that the impact time is around 10 to the -2. So there will still be a force of 10 to the -3. So if you compare it to the mass of the ball, the acceleration will be very high.
Okay.
Oh, sorry, 10 to the +3. Yeah.
Thank you.
Okay, I think that's it. So thank you very much, reporter, opponent, reviewer. You can come back. And now the jury has their 5+ minutes for finalizing their grades. And again, I kindly ask you to stay calm and give the jury to chance to follow the scoring sheet. Okay, so time's up, but I think we still want to see all the grades, so we need to get the jurors a chance to finalize the grade.
Ja som im písala včera večer, že nech si to skontrolujú.
Aha, tak si tak, lebo oni si... No, dobre, tak nejak to vykomunikujte, dobre? Ready? 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 Okay. Okay, so let us show the grades for the report now. 5, 5, 4, 5, 6, 7, 4, 5, 8, 6. Grades for the opponent. Now, it's an 8, 8, 8, 8, 7, 9, 9, 8, 6, and a 9. And the grades for the reviewer. Now, it's a 5, 5, 6, 6, 8, 8, 6, 7, 7, 6. Thank you very much. Okay, so we gave a break to Patrick this time. Sergey, you're 4. It will come. Just
hello. Okay. So my partial grades were 3.5, 1.2, and minus 1.7, which amounts to exactly 4. And so the main points were obviously with the what? Oh yeah, sorry. The main points were obviously with the responses to the questions. To every question that you were asked, you were unable to adequately respond. Why you did something, how you did it. And so, yeah, the main fault was in the answers to the questions. That's all I can say.
okay, but we had an 8 as well.
I think the reporter covered most of the basic stuff clearly, even though there's a little bit of shaking here and there, but the basic stuff was very strong, and I kind of liked their presentation. And my partial grade is starting with a 1 and 4.5, and during the discussion, I give them like a 1.5 to 2. That it ends up 7.5, and today I'm actually rounding up everyone, so 7.55 becomes 8.
Okay, okay. If I just can briefly comment, like I gave you some benefit of doubt, but otherwise I would have to go even lower than I went, because I also believe like this was simply like it cannot be. You cannot concentrate a momentum into a smaller piece without giving extra energy into the system. This is like this way it doesn't go. No, it's like you cannot have something which is moving slowly and then take a small part of it and shoot it out without any extra energy. And that's what you claimed was happening in your jet. And this is like physically impossible. For the opponent, it comes back to Claire again.
Many of the questions that the opponent asked was not much of important, and it doesn't actually make the good discussion with the reporters. And then some of the stuff that they spend quite time on, with a bunch of argument about the buoyancy force, I kind of doubt that the buoyancy force is that much important here.
Okay, this is where we deeply disagree, and I guess also maybe with Vitaya, please.
For the opponent?
Yeah.
Okay. I really like the discussion topics that you brought in, the releasing mechanism and also the jet formation with and without the ball, and I think that's very important. And also the how you try to approximate the buoyancy force in order to shoot the ball. So my partial grade is 1.75 for the questions asked, 3 for the opposition speech, and 3 for the discussion.
Okay, thank you very much. For the reviewer, we had 5 by Anka.
So first of all, I think you mentioned the main points. So basically, I almost graded like medium in every category, but I also have to deeply disagree with the fact that buoyancy is not important. So this is where I basically deducted points. And also, I think the slides were a bit chaotic, so it was very, very hard because there was a lot of like running text, and it was very hard to like get an overview on what to look at. So it was a bit, I couldn't really get your discussion analysis. So I couldn't also give many points for that.
Okay, and Georgi managed?
For the like higher end of a 0.8, so I really liked your clarifying questions. It showed a very good balance within like introducing sort of a newish topics and also like clarifying what happened between discussion and the report. So like clarifying questions were perfect to me. I guess I did not punish you like for a technical issue or something like that there was, but like nevertheless, yeah, there's a review of review of the discussion was okay. Like I did not give you plus points in that. What boosted your grades were the clarifying questions and the missed points. In clarified questions, I gave you 2. In missed points plus 0.5, and yeah.
Okay, I think like looking at the grading, it seems to be clear that like the jury is split into within the question whether the buoyancy is important and not, but it looks like most of the jurors believe that the buoyancy force is very important here. But I think that's why we are here, that's why we have that many jurors, and that's why we can continue with the discussion on this topic during the break. Please, we managed to do it in 17 minutes when I said it's 10. We need to have it 10, so let's have 3 minutes break so that we are in 10 minutes back here. Thank you very much. So please, oh, perfect. I see Zofia coming. So let's start the preparation time. You have 5 minutes to prepare, please.
Test. May I begin now? Good afternoon, everyone. I am Yun Zhe from Team Singapore, presenting magnetic gear. We are to investigate the dynamic motion of fidget spinners with magnets attached. I vary the number of arms of the spinner, the orientation of the magnets, the distance between the spinners, the number of spinners, the arrangement of the spinners, as well as the initial conditions. Other relevant parameters include the magnetization of the magnets. Here is an overview of what I will be covering today. Let us begin with the introduction. A line dipole in our magnet can be modeled as a bound surface current, which we use to accurately model our magnets, accounting for the finite size. We can then integrate the field produced by one magnet over the surface of the other magnet to calculate the magnetic force. The total force on each magnet is calculated by summing over all the other magnets, accounting for whether the magnet is attracting or repelling. And the total magnetic torque is the sum of R cross F. We can then write down the equation of motion for each spinner, accounting for air drag and friction. I have experimentally determined the moment of inertia, dissipation constants, and the magnetizations for all the magnets used. Each individual magnetization was accounted for in my simulation. There are two cases of magnetic gear. One is a free motion where the spinners are given some initial velocity then released, and the other is a driven motion where one of the spinners is driven by a motor at constant speed. Let us begin with the free motion. We used 3D printed fidget spinners and non-magnetic ceramic bearings. I used 2 bearings in each spinner to prevent wobbling. We determined the angular positions via image binarization and circle fitting. Here is the angular velocity of the 2 spinners over time, where the right spinner was given an initial kick of angular velocity. We split the motion into 3 regimes. First, the high-speed regime. When the right spinner slows down enough, it enters the chaotic regime where the spinners behave irregularly. Lastly, it enters the low-speed regime where the spinners oscillate about a stable equilibrium. Here is the angular velocities of the spinners for both theory and experiment in the low-speed regime. Taking the discrete Fourier transform, we see that there are 2 main peaks, and the width of the peaks is due to the frequency changing as the amplitude decreases due to damping. We can investigate how the 2 peak frequencies change as the distance between the spinners changes. Here is the theory where the bands represent the non-negligible width of the FFT peaks, and here is the experimental data. We see a downward trend as the distance increases because the magnetic force is weaker. But why are there 2 distinct peaks in the FFT? To explain this, we came up with a simplified analytical theory by neglecting all but the two closest magnets and using the magnetic dipole approximation to write down the linearized equations of motion. We realized that it simply follows the form of a coupled oscillator whose solution is the sum of two cosines with these two frequencies, explaining the two peaks. These frequencies are the frequencies of the in-phase and antiphase oscillations. We can plot the analytical theory on this graph as well, noting a slightly inaccurate but qualitative agreement, and this highlights the importance of our more accurate current cylinder model. Now, let us move on to the driven motion. I used a stepper motor and a belt to turn the spinner. The motor was placed far away to avoid magnetic interference. For most driving speeds, the free spinner will settle into a steady state after some initial transient. In order to find the possible steady states, we ran a grid of simulations. For each driving speed, we start the spinners in a fixed initial position and gave the free spinner some initial velocity. Then we ran the simulation for a long time until a steady state was reached. We can plot the possible velocities reached at the steady state. For example, at a driving velocity of 30 radians per second, there are 4 possible steady state velocities at -30, -10, 0, and +30 radians per second. Interestingly, we can see lines appearing on this graph in the form of y equals to mx, where m can be interpreted as the velocity ratio between the free and the driven spinner. We have experimentally verified that these steady-state velocities are possible as well. The m equals to 0 case looks like the free spinner oscillating about 0 speed. The m equals to +1 case is the free spinner matching in the same direction, and m equals to -1 is matching in the opposite direction. M equals to -1/3 looks like the free spinner going at 1/3 the velocity of the driven spinner in the opposite direction. First, let's explain how the m equals to 0 case works. When the spinners are in this configuration, the net torque on the free spinner is clockwise. When the driven spinner continues to turn, it's spinning so much faster than the free spinner that the free spinner does not have enough time to accelerate. So it stays roughly in the same spot. But now, the torque is pointing in the opposite direction. Hence, the time average torque is 0, and the free spinner does not move on average. This happens every half driving period, and so we should expect to see that the velocity of the free spinner oscillates at 2 times the driving frequency. Here is a plot of the steady-state velocity of the free spinner with a driving speed of 21 radians per second. Taking the Fourier transform, we see there is a large peak at 2 times the driving frequency, just as we have predicted. We also note that the x-axis is in the units of the driving frequency. For the m equals to -1 case, these two magnets are attracting, so when the driven spinner turns, it sort of drags the other spinner along, and this cycle continues, allowing the m equals to -1 velocity ratio. For m equals to +1, the left spinner is given some initial angular velocity, so it can overcome the initial attractive force between the magnets. After it gets past this initial potential hill, the magnetic torque now aids the free spinner in completing the quarter rotation to the next pair of magnets. And this cycle then repeats, causing the +1 case. From here, we can see that as the free spinner turns, the speed will actually oscillate slightly because of the non-constant torque on the spinner as the magnets move closer and further. Because the spinners have 4 arms, this happens 4 times every driving period, so the speed should oscillate at 4 times the driving frequency. Here is the theory experiment comparison for m equals to +1, where we have tracked the initial conditions from the data and put it into our simulation. We see the expected peak at 4, but we also see an unexpected peak near 0, and this peak is not a harmonic. This is due to us being unable to obtain a perfectly constant driving speed experimentally, and I will be happy to elaborate further during the discussion. For the m equals to -1 case, we see the expected peak at 4 times as well. Now, I'll explain the m equals to -1/3 case. In this current state, the torque is pointing clockwise. If the free spinner is matching at -1/3, for every quarter turn of the free spinner, the driven one will do 3 quarter turns. This means that the torque is still pointing in the clockwise direction, hence sustaining the -1/3 velocity ratio. Looking at the trajectory, we see that the peaks are at 1/3 multiples of the driving frequency. According to this explanation, any odd numbered ratio should be possible, such as +1/3, ±1/5, and so on. This is because we used alternating magnet polarities. So if the velocity ratio was even, the torque will end up pointing in the opposite direction, and the average torque will cancel out to be 0, hence the even ratios are not possible. But you might be wondering, why do we only see these steady states and not others? Well, when we decrease the distance between the spinners from 12 to 11 cm, some previously impossible steady states became possible at +1/3 and -3. And this hints at a possible reason for why certain steady states appear. Take the +1 case, for example. When the two magnets separate, it increases the magnetic potential energy of the system, which requires energy. Plotting the trajectory on the potential energy graph, we see that the system is passing through stable and saddle points, and energy is needed to overcome this potential hill. The energy comes from the energy gain from the driven spinner minus the energy lost due to dissipation. When this is greater than the energy to overcome the potential hill, the steady state is possible. Now, I'll move on to some further insights. I have also experimentally and theoretically investigated the case of all magnets repelling, where we also observe even numbered ratios since the magnets are no longer alternating. I have also investigated 3-arm spinners as well as 3 spinners. In the 3-spinner case, we can see periodic steady states with alternating direction. And going to 4 spinners, we see a similar steady state is also possible, which we investigate theoretically. At 5 spinners, the steady state is still possible, but interestingly, at 6 spinners, it is no longer possible. And this is because not enough power can be transmitted through the magnetic force to overcome the increased dissipation. So, to summarize, I have quantitatively modeled my magnets as current cylinders to find the magnetic torque. I investigated the dynamic trajectory and frequency of free motion, and I have qualitatively explained and experimentally verified the velocity ratios for the driven motion for many different parameters. Here are my references. Thank you.
First question, you've mentioned that there is some chaotic state in your system. Do you have any verification? Have you measured the Lyapunov exponent?
Yes, I have. And I have obtained a value of 17.3, which is positive.
Okay, and so what is the procedure? How many iterations did you do? What was the initial perturbation?
Here. So I have verified this by looking at the ln of the divergence between 2 nearby trajectories.
Okay, and so would the Lyapunov exponent depend on initial conditions?
No.
That's true. And so over what time? Here it's flattened. It means you did 1 iteration. In reality, Lyapunov exponent is made in several iterations. So now let's move to your magnets. What is the value of magnetization?
Sorry, let me find the...
Do you have a measurement?
Yes. So I have measured it by fitting the curve. And here are the values.
Okay, how about the moment of inertia of your spinners?
Yes, I have also experimentally measured it by hanging a weight and fitting a curve to the acceleration.
You've said that in slide 43 that the excitation would only be equal to amount of arms. What if the average? What if there would the total field from one magnet would not be zero, like in the case you did?
Are you asking me what is the effect of having non-identical magnets?
Yes.
Yes, I have investigated this as well, and I believe the effect
Okay,
is...
we'll talk about it in the discussion. Okay. How about your driving setup? How did you ensure constant driving frequency? Did you look at how this step is actually constant?
Yes, I have verified that there is only a 3% deviation in the driving speed.
Okay, do you have any verification that the torques, magnetic torques acting in your system are correct?
My trajectory for the dynamic motion of the spinners agree well with the experiment. So I believe my magnetic torque is correct.
Okay, again, please. I know there is a lot to discuss now, but please, if you really need to do it, then do it in a very calm way so that the guys can prepare for the opposition, and then we will see the discussion on the scene. So please, be patient. Okay, the time's up. Please, you can start.
Welcome, ladies and gentlemen. My name is Paweł Ptaszek. I represent Team Poland, and today I'll present our opposition to problem number 10, magnetic gear. First, let's investigate the merits of our presentation. We've seen an investigation of two different types of configurations for both gears, for both when the spinners are free and for driving motion, which is an important difference in configuration. We also this was a crucial part of the problem. We've seen a model describing the magnetic interactions. They looked at how different different models work for cylindrical and both dipole approximation. For free spinners, they have identified 3 phases, and they explained how the trajectories change. They looked at the final state for free spinners. They identified that, in fact, it is a coupled harmonic oscillator, and compared the frequencies depending on the distances between the spinners, which I think is valid because, in fact, it could be a
because it is in fact a coupled harmonic oscillator. They also explained the excitation during the initial phase. However, the middle phase of free motion was totally ignored, which I will talk about in a second. And for the driving, it was also said that they could have gear motion in different steady states, and they explained that different steady states can have different rotational frequencies depending on the configuration of the magnets and their positions and how the magnetic field interacts. So I think it was crucial because this is the part of a problem where we have to investigate the gear ratio, and so that was well explained. However, when you move on to what was missed, the driving regime was totally, half of it was totally ignored because they investigate low velocities. However, the phenomenon is completely different when you increase the velocity. Then there was mentioned that there might be some chaos in this world, the chaotic regime. However, there was no validation. The measurement of the Lyapunov exponent, that's not how you measure the Lyapunov exponent. You have to make several different iterations and measure it. You have to have initial perturbation. You have to make iterations once they reach horizon. When you've seen the plot, it's flattened out, which means they finally reached the size of the angle, the deviation between the angles finally reach its horizon, which means that the angle reached the sizes of the spinner itself. And so at this point, it should be renormalized, and so it was improperly calculated. So we have no proof of the Lyapunov exponent itself. Second of all, his system for driving frequency has 2 degrees of freedom, both in the angular velocity and the angle itself. So there are two Lyapunov exponents, and the maximal should be found to verify that is in fact chaotic. However, this was totally omitted. And so I think it's crucial because once it was mentioned that there is some chaos, it must be investigated. Another thing about the gears. It was mentioned that they act like gears and they found different angular velocities for different configurations. However, they don't always act as gears. If you separate them far enough, the gears phenomena will not occur, and that criterion was totally omitted. There are several parameters that are important here, which relate the inertia of the spinners, the value of magnetization, and the distance between the spinners, which totally affect the criterion for gears motion to even exist. However, this was totally not investigated. Another thing, just to touch on the free spinners, it was told that there are these free phases. However, the transitions from one phase to another was not explained because suddenly the fast spinning spinner slows down and the other one starts rotating. However, the moment at which that would happen was totally ignored, and the middle phase, which is just weird oscillations, were not investigated and were not proven to be chaotic. Thank you. Okay, so I'd like you to show me quickly your slide because you said specifically that your system has chaotic regimes. Could you show me your measurement of the Lyapunov exponent? So, how many degrees of freedom does your system have if you drive it with when you drive one spinner and the other one is free?
I believe the system only has 1 degree of freedom. However, the dimension of state space is 3 because you have the position of the free spinner, the velocity of the free spinner, as well as time because the system is driven.
Exactly. So how many Lyapunov exponents do you have? Is it 1? Like
Sorry, I would like to clarify that this is for the free motion of the transient chaos regime and not for driven motion.
So not only did you calculate it wrong for the free regime, you totally didn't even do it for the driving case.
Yes, I have not calculated it for the driving case because in majority of the cases, the driving motion is not chaotic.
Oh, well, okay, but you've mentioned that regime. It was stated clearly in your presentation, and you have no proof. So once you've said that there's 3 degrees of freedom and 2 of them have Lyapunov exponent, it's the angle and the angular velocity. Do you have a complementary plot like this one, but for angular velocity?
For the driven motion?
Yes. Or if this one was for free motion?
No, I do not. So first...
Well, I think it's really important. You could finish, please.
So first, I believe that I have sufficiently proved the chaos in this regime because by finding at least one Lyapunov exponent that is positive, you will already show that the system is chaotic.
No, that is not true. It's just the fact that it's sensitive to the angle does not mean necessarily that it's chaotic. First of all, chaotic systems must have both the maximal Lyapunov epsilon must be positive. You have only said that it's sensitive. However, do you have any experimental verification that the system is in fact sensitive to initial conditions? I can see that this is your simulation, right? Show me the experimental proof.
Okay, so over here, I have investigated another characteristic of chaos, which is the presence of fractal basin boundaries. So in my free system, which I was talking about, would you agree that since there is some transient chaos, it will be very difficult to investigate the final steady state reached from the initial conditions because it is chaotic, right?
Well, in the end, first of all, just the fact that you're stating that the transition phase is chaotic is inconsistent with the very definition of chaos. I mean, if you left the free spinners to rotate, finally they stop. There is a fixed state, and there are no steady orbits in the free motion. So how can you say that, that it is chaotic motion?
Okay, so I would like to clarify on permanent or rather traditional chaos versus the transient chaos which we see in the free spinner case. I agree with you. In the free motion, the spinners will always eventually stop because of damping. However, this does not mean that transient chaos cannot exist in the free system.
Okay, but can you show me that fractal again? Fractal-like structure? So here you've made a simulation, right? But what physical parameters of the system can you take out from this fractal? Because what are your conclusions from it? How can you determine anything physical from it?
I was trying to show that this system is indeed chaotic.
Well,
and this can be seen from the fact that the basin of attraction is a factor.
Well, I believe that without measuring the Lyapunov exponents, which are our most elementary measure of sensitivity to initial conditions, you have no proper validation. So just because in one certain situation there might be a fractal is not sufficient proof. Okay, let's move on to your steady states. You investigated the gear's motion itself, and in part of your explanation, you had a slide where you showed the potential plots and how the motion how the second spinner moves through these potentials. And so, could you tell me what parameters are important for the existence of gears itself?
Yes. So, if you would let me find the slide. So over here, I believe that there are, like I said previously, you will need to have a power input from the driven spinner to allow the spinner to rotate, right? However, there is also damping in the free spinner. So the difference I'm calling the excess power, and it depends on the damping, which depends on the velocity, and it also depends on the magnetic torque by the driven spinner, which depends on the distance between the spinners, as well as the actual dynamic steady state trajectory.
Well, what you've shown here, you've qualitatively shown a couple important parameters, but you completely forgot one crucial one. Do you think, okay, well, what do you think is the last parameter that you need to fully define the gears criterion?
Could you suggest what that might be?
It's inertia. I mean, if you have a spinner with very high inertia and you rotate this one with the driving frequency that's smaller, the other one just won't rotate. It's another parameter you totally ignored here. And it's important because it defines that criterion.
Actually, I disagree.
But
so
since we've described that there exists a condition for gears, do you have any experiments for it? Did you look at the distance at which the gears phenomenon just stops and they do not work like gears?
So first, I would like to clarify that inertia is only important when you are trying to start the other spinner spinning from zero velocity. However, over here, I am simply investigating what steady state velocities are possible, and so I give the free spinner some initial velocity. Therefore, the inertia does not affect, or rather it minimally affects through air drag. The inertia does not really affect what steady-state velocities are possible, although it might affect whether you might be able to spin up the free spinner.
Yeah, that's exactly what I'm talking about. I'm talking
which is what I have shown
for
here.
gears itself. And so, to just clarify my argument, when there are magnets at a certain distance and the inertia is very small, you can have gears occurring because the other one will be easily rotated. However, if you increase the inertia tenfold, it might be the case that you can't rotate it anymore. And this criterion for gears was not investigated. Qualitatively, there are a couple parameters. Inertia was missed, and there are no experiments. Am I correct?
Yes, there are experiments.
For the condition itself, for the condition for gears motion.
Oh, are you saying what is the critical distance for which the gearing cannot occur anymore?
The critical inertia, the critical magnetization. Have you at all investigated?
I see. Oh, I have not investigated the critical motion, omega needed, or the distance needed. And I believe that it will depend on the various parameters that I have shown previously. However, it is not very easy to gain like simple explanation for the critical distance because there are many competing factors going on.
Oh, it's
For
actually
example,
very simple. You could do it very easily analytically. You could have just looked at the average, because you've shown that to input to have gears motion, you have to, could you show me the potential plot quickly? For the condition for gears, it must be the case that the other spinner stays in that potential well. So you might as well just look what is about the average torque acting on it, and then look at whether for the velocities of the other spinner would it jump out of the potential well or not. It is very easy to make a
Actually, I disagree that
this was totally ignored.
I disagree that you have to be within the potential well for there to be a steady state. If you look at this graph, the system is not staying within one potential well, but rather is transversing between steady and saddle points.
Yes,
and
but it was,
it's not as simple as just saying what is the average torque on the free spinner, because the average torque on the free spinner will depend on the trajectory that it takes throughout the potential plot.
What I was saying is a simple proposal of conditions for the gear motion. However, their conditions were not investigated experimentally or theoretically. So now another thing. You've mentioned the high velocity regime in your free spinner case. Could you please show me your slide with your experiments, your trajectories? So, this is your explanation of why the first one oscillates.
Oh, so I believe this is because...
Could you show me the slide with the trajectories itself? You're showing that there's like an excitation with proportional to the number of arms.
Sorry, are you referring to this slide?
Yep.
I would like to clarify that this is for the driven motion, whereas the previous plot was for the free motion. And I have clearly demarcated this.
Wouldn't you say that the same case could occur for the free spinner? For the free spinner, does it oscillate as well, or does it not?
I agree, and I have shown over here that it is possible. So the right spinner is being driven, and the left one is oscillating about 0 speed.
Okay, so can you give me a prediction? What would happen if it spun even faster, so fast that, incredibly fast?
I believe in the limit of infinite driving speed, the free spinner will simply remain in the same spot.
Yeah, but what if you flipped one of the spinners? Then would you think that would stay in the same spot or start to oscillate? What would happen?
Sorry, what do you mean by flip?
If you've turned around the spinner, one of the magnets, so that the total magnetic field has a certain value and it's not 0.
Oh, I see. So you mean I changed the orientation of the magnets?
Yes, but well, then there would be an average field from the other spinner, and then it would oscillate in that average field. And this gives us intuition about what is important in the problem and how it depends on the frequencies of motion. So here we have this problem is totally different phenomena can occur for different frequency regimes. And the things for low frequency regimes, I think that the presenter did very well by analyzing different gears solution. However, the criterion was totally ignored because magnetic gears don't always work depending on distance and various parameters. Another thing, the middle phase where there could be chaos or not was also completely ignored because they were in verification of the Lyapunov experiment. They didn't have any analysis of the sensitivity to initial conditions, and then when it was attempted, it was done wrongly because there should be two and it should be over several iterations for the condition for the Lyapunov experiment to be correct. And so another thing, for the high frequency regime, there was no explanation of the important parameters here. What happens when there's an asymmetry in the system? How do the fields interact with each other when you, for example, average out the field from the other spinner? And so I think these are important points which were neglected. Thank you.
Good afternoon. My first question, did I understand you correctly, reporter, that you didn't study the initiation of the motion of the second spinner?
Sorry, can you repeat your question?
Did I understand you correctly that you didn't study the initiation of the motion of the second spinner?
Oh, actually, I have theoretically investigated this, and I
experimentally?
show that hysteresis can be observed.
Can you show it?
Over here on this slide, on the left, I slowly accelerate the driven spinner up, and we see that it ends up in the m equals to -1 velocity ratio.
Okay. And is inertia important in this case?
In my theory experiment comparison, it is not important because I am just studying the final steady state
and
reached.
Does the opponent agree with it?
With the fact that steady states can differ depending on initial conditions?
Yes.
Yes, that's correct.
Okay, and the next question to the reporter, can you please briefly clarify when we can get a chaotic motion in this visible?
In the free case or the driven case?
Driven case, yes.
In the driven case, chaotic motion only occurs in a very small band of frequencies near low driving speed over here.
Okay, and how does the opponent think how many Lyapunov exponents should be calculated for this case and studied?
For driving frequencies, the other spinner has 2 degrees of freedom and 1 independent variable, which is time, so there should be 2 Lyapunov exponents, 1 on angle and 1 on angular velocity.
Okay, thank you. The next question to the reporter, have you considered any mechanical damping or mechanical frictions in this system?
Yes, I accounted for both air drag, which is proportional to V, and friction in the bearing, which is constant.
Okay, thank you. Can you open, please? And magnetic friction, yes. Have you investigated the magnetic friction?
Do you mean losses due to eddy currents?
Yes.
Yes, I have. I do not account for that in my simulation, but I have theoretically shown that it will be around 2 orders of magnitude smaller than the other sources of dissipation. Hence, I believe that it is negligible.
Okay, thank you. And if we you investigated several spinners, and what will change if we change the geometry of placing the spinners? Because you place only linearly, and what if we place them in circle, for example?
Yes, so I have investigated 3 spinners in a triangle formation, and because we have 2 free spinners, there are actually 2 velocity ratios for the 2 spinners, and here are the possible ratios that occur at a particular driving speed.
Okay, thank you. Can you open please slide now 19? I'm
sorry.
Oh, okay, okay.
You can watch it here.
Okay.
Okay, once again, please stay calm. It's very hard for the teams to prepare in such a noisy environment. Thank you very much. I understand everyone wants to discuss. I would love to, but we have to stay calm.
Okay, so good afternoon. I'm a reviewer of Team Ukraine, Mateusz Anton, and I'm going to review task number 6, non-contact resistance. Oh, okay. Task number 10, magnetic gear. And according to the task, we had to investigate the motion of the spinners. So let's move on to the report analysis. The reporter studied the different types of motions and qualitatively explained why they happened, and then theoretically studied them and the velocity and obtained the ratio of the velocities. Then he moved on to the really great experimental methodics. The spinners were 3D printed, and they write a lot of amount of parameters, amount of the leaves, the distance between the spinners, etc. Also, they studied the different regime experimentally and investigatively for the free motion and the driven motion, and they studied the low speed regime where they had oscillations, and the chaotic motion and the coupling. However, they only showed the different geometries for high amounts of spinners only for our clarifying questions, and we think that it will be interesting to see in the report. The friction in the system was not discussed, and we only seen it on the clarifying questions. And also the errors were not discussed in their experiments too much. So overall, we think that the theoretical model was very good, and the experimental verification was very good. So let's move on to the opponent. Opponent started with clear clarifying questions about the chaotic motion. However, we think that the amount of them was, and he was too focused on the chaotic motion and during the discussion. And he had a good point, yes, about this chaotic, that they studied a bit incorrectly. And he also mentioned the lack of critical parameters and the conditions that were investigated. However, overall, he had a too small amount of the discussion topics, and the amount of the work was really big, and he discussed only some certain points. So let's talk about the discussion, analyze it. The first question by the opponent was concerning the measurement of the Lyapunov exponent, and the report answered that the exponent was calculated with free motion of the spinners. And we think that this exponent should be calculated also for the driving force to prove the chaotic motions. And we agree with the opponent that they should be calculated, several of them. So also, the next question was considering the importance of the inertia in the describing the gear motion. And we think that the report answered that the inertia is very important only for the starting of the rotation of the spinners. And he was given the angular velocity to all the spinners in the beginning. And we think that the investigation of the initiation of the motion of the other spinners, while the rotation is very important, and it must have been done So the last question by the opponent was considering the high frequency regime, and how it will change if we flip it. And the report answered that they didn't investigate it, and we think that it would be very interesting to study it. So overall, we think that the opponent's questions and speech were quite average, and the discussion and opinions was quite average because they lacked the amount of the topics of the discussion. Thank you for attention.
Concluding remarks, please.
Okay, so first, the opponent and I discussed on the chaos, and I believe I have sufficiently showed that transient chaos is present in my free motion, since one positive Lyapunov exponent is enough to show chaos, and I also investigated the factor basin boundaries. And next, we discussed on the effect of inertia on this system, and I believe that once the steady state is reached, the effect is rather minimal, and we can reach the steady state by just giving the free spinner some initial velocity. And this inertia only affects the transient, which I have also investigated by showing the path dependence of which steady state is reached. Next, we discuss on the criteria for gearing, and I disagree with the opponent that it is as simple as he makes it sound, because there are many competing factors. For example, if I increase the distance, although the potential hill is lower because the torque is lower, the driven spinner will be able to impart less energy into the free spinner. Next, for asymmetric magnets, I have actually investigated the case of asymmetric magnets, and I show that it has a much larger chaotic region. So now, I would like to summarize my report. I have quantitatively modeled my magnets as current cylinders to accurately measure the torque on the spinner. I investigate the dynamic trajectory and frequency of the free motion, and I have qualitatively explained and experimentally verified the velocity ratios for the driven motion for many different parameters such as the distance, number of spinners, number of arms, orientation, and the arrangement of the spinners, although I did not have enough time to show it in my report itself, since I chose to focus more on the qualitative explanations. As such, I believe that I have sufficiently answered this problem statement. Here are my references. Thank you.
Thank you very much.
Okay, please, before we start asking questions, and yeah, Georgi will be the first one, can I have everyone on the stage? Reporter, opponent, and reviewer, not necessarily everyone on the stage. And please, Georgi, your question.
Okay, I have a question to the reporter. We talked about chaos a lot, so, but my question is different. Is there any way to experimentally consider chaos or confirms that there is chaos, just experimentally?
Yes, you can do the same thing that I did to take two similar trajectories and find the average divergence over time. And if you want a more robust way, there are methods in literature which use phase-space reconstruction and delay embedding to sort of estimate what the phase-space trajectory of the system looks like from the experimental data, then calculate the Lyapunov exponent from there.
Okay, thank you very much. Anka?
Can you please go to the slide where you have the 6 spinners in line, where you said that 6 spinners, the transfer is not possible? Which of them was is the left one the driving one?
Yes, the left one is the driving one.
And did you also vary, like, which of them was the driving one?
In this case, no. But I feel like if the driving one was in the middle, then perhaps this would still be possible since there is a shorter distance to transmit the magnetic force through.
Thank you.
Okay, Patrick?
I would like to ask a question to this slide too. You are saying that 5 spinners is possible, but 6 spinners is not. I would expect that it depends on the parameters, like if they are closer or farther. Can you comment on this?
Yes, correct. So I think the important parameter is the distance because it very significantly affects the magnetic force and torque on the other spinners.
Please.
So I have a question for the reporter. So you mentioned at the end you have a situation where you can have like 3 spokes instead of 4, but you have like alternating magnetization.
Yes.
So I was wondering how that like asymmetry.
Over here. So we see that there is actually a large region where the system is chaotic. And here is a plot of the trajectory.
Wonderful.
Okay, thank you very much. Eric?
In the case of the freely oscillating system, do you observe nonlinear effects or third order terms in the expansion?
Yes, so the linear approximation is only to provide some qualitative understanding. And if we take the spectrogram of the signal, we see that the frequency is actually increasing as the amplitude decreases, which showcases the nonlinear effects.
Okay, I think it was slide number 44. You had this small, yeah, that one. You mentioned you could comment on that, the big peak, very briefly.
So over here, when we plot the trajectory comparison over a long time, we see the theory reaches a steady state, but the experiment does not. And this is because of the slight variation in the driving speed experimentally. So because we put the initial conditions into our simulation.
Okay, and the 3%, that's just like your engine is not enough or whatever, like this 3% deviation.
I think it might be due to the tension in my belt not being super strong.
Okay. Patrick?
On, I think, slide 19, where there was the free rotation, yeah, here. Why do we have these huge errors in the theory? Okay, yeah.
Oh, like I explained in my slides, this bands is the width of the FFT peaks. And the peaks are not sharp because the frequency changes as the amplitude decreases because it is nonlinear.
Okay, Eric?
Question for the reporter. If you are in the gear mode at high frequency and you successively lower the frequency, do you ever drop out of the gear mode, and when does this transition occur?
Are you saying if I have, let's say, a velocity ratio
You modeled the upwards acceleration of the motor, but what if I go down So start at high velocity in the gear mode and then lower the driving frequency.
Oh, in this plot, I don't actually start the spinners from 0 velocity. I give the spinner some initial velocity and I see what possible steady states are reached. If you drop down, yes, you do.
Okay, any further questions? If not, then yeah, again, thank you very much. Let's give a big applause for everyone.
Thank you.
Please come back from the stage, and again, it's almost the last time for you to need to be quiet till we finish our job and let the juries. I just take the liberty in the meantime to give you some technical comments. After we finish here, we are a bit late, but not too late, so we'll have almost 1 hour for lunch. The closings, the lunch is outside, just where you had the refreshments, but it's a full proper lunch. If you prefer being seated during your lunch, then 1 floor up there are also seating tables, so you are free to take your lunch from the buffet area and then go up and be seated. Very importantly, we will start the closing ceremony 3 p.m. sharp. That means everyone has to be here 3 p.m. So we will try to get you in, but if you are helping us by just like moving towards this room 5 to 10 minutes before 3, it would be great. I think you'll have like more than 45 minutes for lunch should be enough. We will try to make the closing ceremony not too long, although we have some things to give you, and it is not just certificates and medals. And again, not having too much time on during the closing ceremony, I would like to mention that this is the first year where we have almost real money prizes for the participants. By almost real, I mean they are like Bitcoin prizes, but like some of you will get some Bitcoins from our Vincent sponsor. So you get some envelopes. Importantly, you get some envelopes, but the envelope, it's just to key to get the Bitcoins, and you have to apply for the Bitcoin till I think 12th of August. So like within a short time. If you don't do it, they won't be there anymore. So if you get an envelope, don't forget to open the envelope and apply for your prize. Okay, sorry, but like they also like, you know, I don't think we have special Bitcoins just for us. Okay, please calm down. What? This was quick. I understand everyone's ready. Yeah. And then let us show the grades. Oh, no, sorry. My fault. Okay, I do apologize. I looked on the partial grade, saw it filled, but I didn't realize it's not summed yet. Okay, but now we are ready. So let us show the grades for the report now. 8, 9, 8, 9, 9, 9, 8, 9, 9, 9. Grades for the opponent now. 6, 5, 5, 8, 9, 7, 6, 6, 5, 4. And grades for the review now. 6, 7, 6, 8, 6, 6, 8, 6, 7, 6. Thank you very much. So it was like extremely close for the report. So anyone who would like to comment, you are welcome. Georgi, please.
If you'd like, I can start with the report and then continue with the high grade of opposition.
No, I think someone else has to comment for the report as well. So
okay.
Please.
Okay, for the report, what I say is that the solution was like almost perfect. You did like many extra things, and all the solutions and all the regimes were quite interesting. I agreed with the opponent with the chaos part, but like I did not take much grades from you because of that. Like it was not much part of the problem, and like but like, it was still important, and that's why like I did not give. If you had like it perfectly, I would have given you a 10.
Okay, and maybe an 8 by Sergey.
Yeah, so it's strange that I have to defend like a low grade. So yeah,
I took the opportunity, but this is really rare.
Yeah. Okay, great. So yeah, basically this is my comment. You did really well, and so I gave you a lot of points for what you did. But there were also many things that were stated in the statement of the problem that you did not do. And yes, you showed that you did also those, but it would be nice to see in the report at least an overview of your findings, even if you didn't show all the basics, all the experiments, just the findings, so that we know that you did it and what the main takeaways were. But I appreciated a lot your explanation of the phenomenon also.
Yes, I think the task was very broad. I was very wondering that someone selects this one for the finals, because I couldn't imagine how to solve such a broad task. And I think to get a 10 from me, it would be nice to have 1 or 2 slides giving you impression like we have done this, but we would need like 5 days to explain everything. So we go into this detail, and that's what we tell us. But if you're interested in like this is the rest, I think this would make 1 point more maybe from other people. Yeah, now I go to my 4 for the opposition. I was between 4 and 5, and basically I took notes on how much from your speech, how much from the discussion especially was focused on what was presented. It was very little. The first slide, which was opened here, which was presented during the presentation, was opened after minute 9 in the discussion. Like all the time, you basically discussed things which were not presented in the presentation. Chaos might be very interesting, but this was not their point. No, they just managed it and mentioned it and went further. So for me, I really considered both the speech and the discussion as not very relevant, and I also subtracted you points for the way you pursued the discussion, because in several cases you didn't let them speak where it would have been appropriate. But we had 9 as well there.
Yes, yes. So I partially agree with Martin about like what that you could have focused, and an opponent should focus more on the report and what is happening there. I would have like strictly punished you because of it, if only like the report and everything was not almost perfect. So if I did not get anything like from the report and you did not focus on it and instead like talked a lot about chaos and other things, and like yeah, that would have been a large issue with me. But I went so high up because you showed that you understood the physics and the problem very well. With the chaos, I think that you were completely right with the calculations of Lyapunov exponents, and it had to be done with iterations, and it is a finite time Lyapunov exponent, needs to be calculated. And with the reporter, I think like you mentioned 17.3. And yeah, that is too much for this layer. Like
okay.
I think between like 0.11, I don't know. But yeah, that is like in every aspect you showed a very good knowledge of physics, and yeah, for the discussion it like lighted everything up, and it was really fun, and
okay,
that's why I went.
Okay, thank you very much. We have like 2 seconds for Eric for explaining his 6 for the review. No, you can get a bit more.
Oh, that's nice. So for the review, I thought it was a rather average performance. So on the plus side, for example, I liked that you highlighted that the discussion on the chaos took a far too center stage. However, for example, for the review of the report, you were extremely vague. For example, the weaknesses you had the friction basically, and it was one of the main weaknesses. But they were, I think, far bigger problems in the presentation. The presentation was not perfect. There were things too that you could definitely add to. So I gave you 1, 1.5, 125, 125, 0, 0, which gives 6.
Okay, thank you. But Carrie, you liked it more?
Yeah, just a little bit though. Really, not very significant to Eric's. I gave it 1.5 for the questions. I'm like a little bit 0.25 better on everything. I thought it was a nice review. I liked the questions. It was it was just quite good. Nothing particular I wanted to draw out. You mentioned the overuse of the over-focusing on chaos, which I thought was important, and you generally talked about the few things that were missing and gave credit where it was due. So
okay,
it's pretty good.
Thank you much. So let's have another big round of applause. And now I just invite you for lunch, and let's meet here in less than 55 minutes.
Hi, welcome back. We have a very special final day planned for you. We're going to hear from some special guests, and then, of course, we're going to give out the prizes to all of the participants. So, without further ado, I would like to invite Matyas Pocha, Director of Innovation Ecosystem at the Bosch Group here in Hungary. Thank you.
Thank you. Dear Minister Hanko, dear President Plesch and Hömöstrei, dear jury members, dear teachers and students. On behalf of Bosch Group in Hungary, I extend a warm welcome to everyone at the results announcement of the International Young Physicist Tournament at our Bosch Budapest Innovation Campus. We are proud to support this highly respected professional and international event and host key stages of the competition here at Bosch Budapest Innovation Campus, which is the home of future automotive developments. The pursuit of continuous innovation is rooted in the century-old legacy of our founder, Robert Bosch, whose entire life was driven by a thirst for knowledge and desire to achieve better. This drive helped him through the toughest times and inspired him to continuously turn new ideas and concepts into reality. This resulted not only in innovation products that continue to be significant in the automotive industry and other technological fields, but also led to the birth of Bosch, the global company we know today. At Bosch, we focus on the future of innovation. We clearly see that comprehensive innovation can only be achieved through partnership with others, academic institutions, universities, startups, other industry players, and with you as the representatives of the next generation's young talents. That is why we have been placing a strong emphasis on building Bosch's innovation ecosystem in Hungary for years. As part of our diverse programs, we provide opportunities for the generation of high school students to learn about the development we are working on here in Budapest, or at the Bosch plant in Hatvan, Eger, Maklár, and Miskolc. We also value initiatives that equip future generations with up-to-date knowledge and skills essential for their professional development. The competition concluding today is one such initiative. Congratulations to all the students for their excellent performance and achievements. I hope that in the future we will see many of you not only as guests at our Bosch Budapest Innovation Campus, but also as future members of our Bosch team. On behalf of Bosch leadership, I would like to thank all the organizers and supporting partners of the competition for the cooperation. Thank you for your attention.
I would like to invite IYPT President Martin Plesch to give a few words. Thank you.
Your Excellency, colleagues, the participants, team leaders, jurors, guests, you have seen me here the whole morning, and I'll be coming regularly back the whole afternoon, so I don't really want to speak a lot. I would just like to thank you, Minister, and the whole ministry and also like the Bosch company to allow this all to happen. Because as you see, with this amount of people and with the complexity of the tournament, these events can't happen without major support from the governments and from big companies. So it's very important for us as the organization that we see the support and that we feel the support. And I also hope that you could see that like this is something that has a very high quality, and then everyone who is sitting here among the participants, but also among the team leaders and jurors and the organizers, is someone who is contributing for making the society better and stronger in that way. So once again, thank you very much for letting it happen. And
I would like to invite co-chairman of the local organizing committee of Hungary, Mihály Hömöstray.
Hi everyone, again. Hi, welcome to the newcomers, Mr. Minister and Mr. Mátyás Pócsai again. But first of all, I would like to talk to all the participants in the name of the local organizing committee. I hope that you have a lot of things to remember, a lot of memories, a lot of things to tell later back home. All of us have different memories of this competition. Maybe I can mention maybe the heat is one of the common ones. Hopefully also the food is also a common one. I'd like to hope that all the fight rooms and whatever happened in the fight rooms is also a very common one. Hotel and dormitory is more or less something different in our minds, but life is different, world is different. I hope that still all together you could get a very positive week and very good memories. From my point of view, this week was mostly about learning. Again, as teacher, for me is obviously one of the most important things, and I would like to thank you that you were here and made it possible, that I had a lot of things to learn. And beside that, I had to work a lot. It's more or less clear for all of you. It's not just work of the participants, but it's also work of the local organizers. And therefore, I really would like to ask you for a huge applause for all the fight room assistants, guides, and other organizers, because they had an incredible job in this week with all the counted and unpredictable problems we had to solve. I'm really proud of them, and I hope that you are as well. So please. And surprises are always surprises on an IYPT. I think you have to learn that for the next IYPTs. For me, it was, for example, the global sponsoring of Vincent, and I was also learning a lot of them, because they can maybe make me rich on a day if I use their tactics. And I really want to mention it, that all the participants with some medals, they're gonna get a surprise also from Vincent, which is, I think, also a big thank you for our global sponsor. But I think it's time to move on. We're gonna see us on the gala dinner. Thank you again.
Okay, it is now my great honor to invite to the stage our special guest today, Hungarian Minister of Culture and Innovation, Balázs Hankó.
Thank you so much. So, hi everyone. So, dear President, dear participant, and all of you young physicists. It is an honor for me that I stand before you today at the closing event of the International Young Physicist Tournament. Over the past few days, we have witnessed the competition of young minds and talents that has not only been inspiring, but has set an example for all of us. First of all, I would like to thank everyone who contributed to the success of this event. Special thanks to the organizer, to the jury, and the sponsors, of course, without whom this event would not have been possible. Thank you all the students who came from all over the world to make and to take part in this prestigious competition. During the competition, we witnessed many impressive performances. Each student showed the science and the learning can be unifying force across borders. The presentation, experiments, and solutions all prove that the future is in the hands of talented and dedicated people such as all of you here. That's why the government has the responsibility to support and encourage efforts that move science, technology, and life of our nation toward progress and development. This must mean not only financial support, but also moral and professional support as well. We have reason to be proud, as not only our team, but Hungary as a whole has performed well in this area. We have improved our ranking in 2023 European Innovation Scoreboard by moving up to a higher category from emerging innovators to European innovators. It is an important milestone that the John von Neumann program, approved in 2023, will now link universities, researchers, and research centers and the economy to improve the competitiveness of the latter, thus increasing the number of researchers, even young researchers, developers, the number of patents, and the innovation potential of small and medium-sized enterprises. In recent days, we have experienced how inspiring the international environment can be. In order to provide this feeling for every student in Hungary, we launched the Pannonia program, which provides mobility opportunities for 8,000 students. And also for Hungarian researchers and Hungarian higher education ecosystem, we introduced the Horizon program for 8 billion Hungarian forints. Ladies and gentlemen, young physicists. Scientific research can often be challenging and sometimes frustrating. The great scientists we look up today also faced many difficulties. We can see from the examples of the Hungarian Nobel Prize winners, Katalin Karikó and Ferenc Krausz, and it's a great opportunity that you had the chance to listen Ferenc Krausz professor as also a young physicist. This diligence also shown by the results of the Hungarian team, who in addition to forming a real team thanks to the excellent teamwork between the members, finished in 10th place, also won the best bronze medal. So thank you for the Hungarians. Studying physics is not just about expanding our current knowledge, it is also the basis for future technologies and discoveries. Young physicists, you are the future. I hope you continue to find joy in discovery and that you continue to find answers to the biggest questions in your work and in the whole entire life. Be brave, curious, and committed. Congratulations to all of you. Thank you. I stay.
Yes, I'd like to invite Mihai Hőstre back to the stage, along with Minister Hanko, and they're going to give out the special prizes of the local organizing committee. The first prize is Extraordinary Review from Team China, Xiaoxi Zhou, Problem 11, Pumping Straw. Congratulations. The next prize is for Extraordinary Opposition from Team Brazil, Cao Francisco Macedo Alejo. Congratulations. And finally, the Extraordinary Report Prize from Team Slovakia, Luisa Lea Lavrikova, problem 17, quantum light dimmer. Congratulations. Okay, thank you to Minister Honko one more time. Okay, I would like to invite IYPT President Martin Plesch back to the stage. And now to give away the participation certificates, I would like to call the teams and team leaders in order. In 38th place, the teams and team leaders from Kazakhstan, please come up. In 37th place, Team Uganda. In 36th place, Team Turkey. In 35th place, Team Croatia. In 34th place, Team from Iran. In 33rd place, the team from Nepal. In 32nd place, Mexico. In 31st place, Slovenia. In 30th place, India. In 29th place, Italy. In 28th place, the United Kingdom. In 27th place, Pakistan. In 26th place, Romania. In 25th place, Macau. In 24th place, Greece. In 23rd place, the United States of America. In 22nd place, Hong Kong. In 21st place, Austria. And in 20th place, Czech Republic. I would now like to invite Mihai Hömöströy back to the stage, and we are going to give out the awards to our bronze medalists.
Do you hear me? Oh, okay, now it's working. Okay, you probably realized that we were sneaking out of telling like how much you get. It's because it's Bitcoin, so you never know how much you get. But so as for now, the bronze medalists will get like per team member, not team leaders, per team member something like 175 euros.
Okay, in 19th place, Sweden. In 8th place, 18th place, Thailand. In 17th place, Serbia. In 16th place, Canada. In 15th place, Australia. In 14th place, Brazil. In 13th place, New Zealand. In 12th place, Georgia. In 11th place, Korea. In 10th place, Hungary. And those were our bronze medalists. We are now going to move on to our silver medalist, and to help us give out the awards. Yeah. Right? Yeah, I would like to invite to the stage Adrian Ranga, Head of Unit of the Science Policy Department of the Hungarian Ministry of Culture and Innovation, to help us give out the awards.
Okay, and we doubled the amount for the silver medalists, so it's 350 for each.
In 9th place, the team from Bulgaria. In 8th place, the team from China. In 7th place, Switzerland. And in 6th place, Slovakia. Fifth place goes to Germany. Thank you very much. Thank you. I would like to invite Mihai Hümöstri back to the stage so that we can now award the gold medalists, starting with, dun dun dun, number 4 is, nope, oh, sorry.
Okay, someone asked me the prizes I gave out, whether it's in forint. No, it was in euro. And yeah, we double again, so it's 700 per participant in the final. And the place number 4?
All right, okay. So let's get to our gold medalists, starting with number 4, Chinese Taipei. In third place, the team from Poland. Second place in the tournament goes to Ukraine. And now, the winners of the 2024 International Young Physicist Tournament is Singapore.
And for the very champions of the IYPT 2024, the local organizing committee has also prepared, I would say, pretty nice extra cup for the champion team, in this case, Team Singapore. Congratulations. Open it? Yeah.
Last but not least, we have this cup which is rotating, not really much once you are back, but it used to rotate among the winners of the IYPT, and now it comes back again to Singapore, so back home. Congratulations. Maybe you can pass. Take care, this is glass. Congratulations. And it was renovated by the team of Poland. Thank you very much for that. So I hope we can live with it now for another like 25 years. Okay, it's almost done, but it's not entirely done. Most of the people sitting here around were marching here in front of us, and that was about you, no? Team members, team leaders, working all the year hard and preparing your presentations, and then working all the day and night hard here to present it. But there is also the other part of the scene, and these are the jurors, like those people who are usually not really praised by you, because not everyone is always entirely happy with their grading, but still these are people who really work hard. They come here often throughout the half of the globe and sit in the juries and work hard. And I would really like this to use this opportunity to thank them and really to ask them to come, all of you, on the stage, so that everyone can see how many jurors we had in this tournament. So please, all the jurors come here now. And let's give them a big applause. And while coming here, I also have to mention that Vincent again prepared a nice gift for every single juror. But please come here so that everyone can see the amount of persons that work hard during this competition. I don't think you'll fit in one row. So it's just like, first I was told you cannot come on the stage because it would crash, but then like we decided that it should hold. But like, please go on. It's just like, come on, guys. I got like strict 5 minutes for this idea. So. Yeah, you can come in the front also a little bit, so that we can get a nice photograph of every single juror. Come in. So enter the bus. No, it's like that's what they always call. Okay, so all these men and women worked so hard during the competition that we can run the competition. And I would once again like you to give a huge applause for them. So please. Yeah, let's make a good arrangement for the picture. And once the picture is done, when you... Yeah, thank you very much. Oh, yeah.
Bit closer, please.
Someone can lie on the... Miha, you are a party maker, no? Yeah. Okay, thank you very much. And while leaving, please, everyone gets a don't rush. Everyone gets a bottle of Slovak honey wine. So when leaving, just take your bottle. No, there are persons prepared to hand it over. Thank you very much. Yeah, both sides are fine. Both sides are fine. If anyone cannot transport the bottle, you can leave that way as well. The bottles are expecting you. Please, please. If anyone cannot transport it back home, see the local organizers. I think they'll be happy to get one bottle for them as well.
Mondom, hogy akkor meghívom Martin, hogy zárja, és aztán... Igen, lassan megy, ott marad. Oké.
Okay, I think we are done, and this was almost it. I just, Mihai already thanked to all of the local organizers, guide, flight assistants, etc. So I would also like to thank all of you. Köszönöm szépen. It was very, very nice to see, because at the beginning it was like, oh, we don't get these local people, you know, it's holidays and they won't come, etc. And in the end, like, there was an enormous amount of people everywhere. Whatever we needed, immediately someone was there to come and help. This was really great to see. And yes, another applause for all of them, please. And there were 3 persons which worked very hard since a very long time, and I would like to call here to join me on the scenes. Mihai, Peter, and Zita, please. You know, like, these guys were always running there and back, and yeah, I have to say, like, Peter was the one we always approached, because if we needed something, then Mihai was like, oh, and then Peter was sure, and then Mihai was, Peter did promise it you, okay, then we'll do. So, and Zita was also always like helpful. Okay, guys, thank you very much. It was probably you didn't expect to come that many people and that many countries to come, but you managed to organize everything really great. You know, like in the Olympics, they always used to say it was the best Olympics ever, and then at one moment they had to stop to say it. So I don't even start this tradition, because then it would be bad to stop it. But it was certainly one of the best tournaments we ever had. I would like really thank you very much for it. And yeah, we are keeping the tradition of giving Slovak gifts. We have small fight with Hungary, like historical fight about this very special type of wine. It's called Tokaj wine. And, both Slovaks and Hungarians think they produce the real Tokaj wine. So we bought the real Tokaj wine for these guys to see. Okay, no, anyway, we have some wine for Peter and Mihai, and we have some sweets and some flowers for Zita. Thank you very much. Thank you so much. Oh. Thank you very much. Okay, Peter, Zita, thank you very much. And Mihai should stay here, I guess. I'm coming back. Yeah, so Mihai will come back. And may I invite a representative from Sweden? Lars. So you'll be the responsible one. So it's a tradition that at the end of the tournament, we always have to pass the flag of the organizer to the next country, and it will be Sweden. So before I do that, I don't have to forget, so I'll declare the 37th International Young Physicists Tournament hereby as closed. And we pass the flag to the next organizer. So let's meet next year in Lund in Sweden, I guess.
Yes. Should I say something?
Please. Oh yeah. Okay. Mike is coming. Is this one?
So, thank you. On behalf of the LOC of Sweden, we are honored to get this bid. We are excited and maybe a bit nervous to organize such a thing. I think Mihai is rather relieved right now. And our butterflies are starting to take off. I can't promise anything about the weather. Just that Sweden or Scandinavia is located between the Arctic and the intermediate circulation zone, which means the weather is rather changeable. You can have rain, rainstorms, and rather warm Swedish conditions, Swedish standard, which means about 25. 30 happens, 37 I think I have encountered once in my lifetime. But you never know these days. But I welcome you all to Sweden next year. See you then.
Thank you very much. And then just one very last thing. I know all of you are tired now, and probably many of you have enough of IYPT or whatever. But when you come home, maybe you feel like, oh, maybe I would like to continue. Some of you can continue, that's great. But some of you don't because you go to your universities, etc. I just wanted to mention that there exists a competition which is called International Physicists Tournament. It's for bachelor students. It's of the very similar styles than IYPT. And we have representatives of this competition around. So if you are interested, you can meet them during the gala dinner today and discuss with them how to join a competition. Thank you very much. And I pass the word to Steven.
That's it. Go. What are you doing? See you all tonight at the Durerkert for the final gala dinner. See you then. Everybody, bye. Great meeting you. Well done.